Well, here we are. Today is September 9th, 2023, and we're having our 41st Zoom meeting of the FORCE 2020 group with an exciting schedule ahead. And so let me see if I can pick it up, or Peter, maybe you can share it. I have it on the other computer.
Let me see.
Yeah, so that would be great. So we have exciting talks ahead with Brett Rodriguez, with Virgil, with Pablo, with Brett Nelson and Bill Ragsdale. There we are. And just before this recording, we had the FORCE Cafe a chat of different things that people found interesting. So very nice stuff indeed. So yeah, I would say yeah, maybe we didn't actually talk about that, but we have very sad news that appeared. Yeah, we have the situation that our dear friend just died and passed away in a traffic accident. Howard Oakford. So that is very sorry, very sad news on our side. And so this was completely unexpected because he was so eager. He just moved to a new place and wanted to spend the rest after retiring there with a new flat and whatsoever. And this was an unfortunate bicycle accident that Howard was involved in. And he was seriously injured and died 2 days afterwards in the hospital. So that's very sad. And you all probably know his famous talks about color force. My favorite was always the magenta variable, which is a special feature that you don't find anywhere else. So that's actually really great. Yeah, so we're so sorry and he will be missed very much. I met Howard also in person when he was at the local FORCE meeting, and I met him at several Euroforce conferences. So, and being born in Great Britain, he shared that typical humor. So he was always very polite and humorously could explain things with some understatement. Actually, well, I don't know about that, but it turns out after discussing with him that he was a really expert in that. And yeah, so he promoted many great ideas, and he was especially fond of color force and released a color force version every year that he offered to the community so that people could go ahead and try out, addressing also colorblind people with a black-white mode, and also those people that like the traditional keyboards, going from the original character set to the ASCII character set, and many other things. And he
Ulrich, I would
yeah.
like to say that Howard was, first of all, a gentleman,
Yes.
a very nice man, super fantastic. He never was, he always helped the community very much. I am the reason I am doing the FORCE meetings and that we have a FORCE 2020 group is because of people like Howard, and especially Howard, because he, when I had a problem learning Win32 Force, he was in the community active, and he developed a lot of Win32 Force. And
Yeah, right.
his answers were super professional, and he never entered into you never had a sad answer from him. He was very humble and incredible gifted programmer. Yeah. He was a fantastic
I agree. Very friendly indeed, and very helpful and gave lots of helpful comments. That is right. And you mentioned it. Win32 was his second thing he took care of, contributed there a lot of things in that community as well. So yeah, I'm so sorry
Very
about his
sorry for
sudden
that.
death.
Yes, very
So
sad.
and he really has been ripped off his life and out of our lives, and he just wrote a notice that I'm so excited, I'm doing new Forth things in color Forth and on the Forth level, so many new achievements I've done, I would like to report, and now they are not found. So yeah, and we'll have to see how we can actually deal with
the site is not there, but
the site is no longer there.
Of our friends, some of our friends recorded the site. I think Alex Dumont recorded the site on GitHub, and someone else also told me he recorded the site on, I think, Cornelius. I don't know who told me.
Yeah. I think we will be able to reconstruct what he has, what he had provided, even if his site is no longer available. And we will see, maybe we can find some way to contribute to his life. Yeah, so he will be missed very, very much.
Very much, yes, we will miss him.
Yeah, and he was regular participant in our group as well. So you probably heard him talking, and you know what I've been talking about. Right. So
really quick, the site is still up. I just went there through the main URL, and it's showing up. Maybe the link that you used led to an unknown page, but the site is still there. So whoever feels like grabbing another copy, please do.
Excellent. I will change the link and then.
Right. Okay.
Thank you.
Anyone else want to say something about Howard? All right. I think it is in his spirit that we deal and continue to deal with Forth. And so I would kindly ask Brad Rodriguez to give his talk on TTL Stack CPU with Forth. The second part, we heard the first part, I think 2 months ago. And I'm very excited to learn more about that. So Brad, if you are, I saw you already, and yeah, you can take the stage.
And my audio should be live now.
Yeah.
Is it?
Yes.
Okay, good. Well, thank you, everyone. Sorry. Thank you, everyone, for inviting me back. I don't think this is quite intended to be a two-part talk, but part of this talk. There were a lot of questions which I didn't have an answer for right away, so I said, I'll have to get back to you on that. I'll have to think about that and get back to you. And today is the getting back to you part. So there were some amusing elements, I want to say last presentation when I spoke in October, and I hope to bring those out a little bit more too. But first, let me end the suspense, because I found the original PISC prototype that was done in wire wrap and had EEPROMs dated 1993, which caused me to wonder if it is possible that they would hold their data that long, and the program for the PISC. And I remembered that the last thing I left on it was a continuous memory dump program. So that you turn the thing on and it just starts dumping out what it sees of memory, and that's actually a useful diagnostic in many ways. Last night, not this morning, last night, I finally got all the cables and everything put together, and without any further ending the suspense, there you have it. Turned the thing on, and it immediately started running the memory dump program. So we know at least the EEPROMs are good for 30 years. I don't know about the rest of it. Can I back away just enough to see? I'll come back to this later, but especially because I don't have enough headphone cord for this. But the video monitor is displaying the dump program. The board, where is there some light? The board between the video monitor and this green card, that's the PISC computer. And this green card is the video card that I had from another project, another personal computer, actually. It's unusual in that it's a television typewriter style of board, but it has a parallel input. It has an 8-bit parallel port to talk to the processor. And also it was a spare that I had lying around and wasn't using it. So there it is. The suspense has ended. It will actually run after 30 years. Now I have to find something else to run on it. Unfortunately, I have not been able to find that dump program or the microassembler I used to write it or the specifications of the microassembler. So I'm in the process of reconstructing all of that right now. I may have to start looking in my shelves and see if I have a computer from 30 years ago, which might still have the source code on it. But let us continue. Now I need to share my screen. Okay. Ah, there we are. Select window. This should be, I don't get to see it, but this should be the first slide of my series of slides. Instruction set computer, episode 2. It lives because I'm calling this episode 2 because I think this is going to be episode after episode until I'm in the grave. So this has been my longest thriving project I've ever done. Okay. This is, by the way, part of the fame. Imagine my surprise. I was looking online for something about the PISC. I did an online search and I found a reference to an article at Y Combinator. It's actually a user post at Y Combinator. For those of you who don't know, Y Combinator is a fairly famous startup accelerator, tech startup accelerator. They're not so much a venture capital firm, but they provide expertise and guidance to get your tech startup going. They've been around for quite a while. And they're fairly prestigious. So even though this was just one of their users posting onto what is the equivalent of Slashdot, I was tickled to see that. I think I have enduring fame now because my work has been discussed in Y Combinator. But on to the work. There we go. I left this slide here in case we want to refer to it. That is the Model 1 pathetic instruction set computer as is running behind me on the board or on the table. I made last time an allusion to a 17th microinstruction bit. And there was also a question about, are there possible hardware conflicts on the data bus? First, I want to distinguish between, well, let me say that a microinstruction bit is usually thought of as every one of the hardware signals in the processor is controlled by a specific microinstruction bit. That's not universally as microprogrammed and what is not. Top half of this slide, the two NAND gates for memory write and memory read, those are not actually changing any logic. They're not changing any functions or providing new functions. What they're doing is conditioning the read and write signals that are sent to the memory chips with a clock. So that instead of not MWR or not MRD, instead of them being active for a full 200 nanosecond instruction cycle, they're active for the last 100 nanoseconds of the instruction cycle. That is to give the adequate
So, Brad, your voice still or drops out like earlier, so maybe you switch off the camera. Oh, to me, his video is frozen anyway. Here we go. Still can't hear you. No. There's silence. I don't know what the issue is right now. Here we go. Some fragments of your voice.
Me at all. No, this is a problem.
Better.
Okay.
Better now.
Well, I paused the screen sharing. Okay, I paused the screen sharing.
Well, it's
Can
better
you
now.
see
It's
the
now,
last
it's...
screen or? Okay.
Yeah, so we still have the 7th micro instruction bit on screen here.
Okay. I'll resume at the top of this slide then. The memory write and memory read signals are conditioned by the clock signal, so that rather than being a 200 nanosecond wide pulse with no setup time, now the memory strobes that are actually going to the memory chips have a 100 nanosecond setup time and 100 nanosecond read time or write time. So that's just about timing. That's not the 17th micro instruction. What I had in mind was at the lower right of this design diagram, excuse me, there's a not WEC. That's write enable C, which refers to the C port on the memory file, register file. Let me try to go back a bit. There we are. The C port on the register file, which is on the right side as is drawn in this diagram. That has a write enable function. Ordinarily, we would write, whenever we're doing a memory read, we're doing a write to the register file. So it's memory read, writes to the register file, register 0, and a memory write. If I have to write something out to external RAM, read of the register file. So read enable C. So memory read just provides read enable C directly because it's not the read strobe, it's just an enable. The data is latched at the end of the clock cycle. But we condition the write enable C such that the not fetch signal has to be true. We don't enable writes to register C when we're doing the instruction fetch. The instruction fetch data from memory goes just to the instruction register, not to register file, register C. So arguably, by the strictest definition of microprogram machine, I should have made WEC a separate signal instead of having it combined result of MRD and not fetch. However, it's one NAND gate. I don't think that's contributing a whole lot of logic to the design, so I'm continuing with WEC not. I'm continuing with that being a derived signal and not directly from the microinstruction. The potential hardware conflict, I forget who brought this up. Is it possible for there to be two different sources driving the data bus, two conflicting sources driving the data bus? And how could that be protected against? And my immediate offhand remark was back in October was that, well, yeah, there are two different things that can drive the D bus. One of them is the register file when MRD is active. Excuse me, when MRD is not active. And the memory read, actually reading from the external memory when MRD is active. Well, it turns out those two conditions, the way it's derived here with this added bit of logic, those two conditions cannot happen at the same time. For the read enable to output data to the D bus, MRD must be low. For the memory interface, which is the buffer and the RAM and ROM chips, for that to output a signal on the data bus, MRD must be high so that not MRD can go low. That's strobe. So it's protected against that hardware conflict. That I'm sorry, I've forgotten who asked about that, but that is resolved already. That conflict cannot happen. And if you want to work through the combinations on this logic. I'll jot it down quick because I'm about to move to the next slide. Whoops, next two slides. One of the things that caused some amusement last presentation was how you do a branch in a machine that doesn't have a branch instruction. And this is it. This is a conditional branch at the microcode level. It takes 5 instructions, arguably 4. The way we take a conditional branch, we read the status on the carry. All external status is read on the carry pin. That's the only status input the 181 has. And so we have an instruction, which is a lovely instruction, -1 plus carry, which will set the, in this case, W register to -1, which is all 1 bits if there's no carry, or set it to all 0 bits if there's a carry. So this gets W as all 1s or all 0s, depending on the carry input status. We invert that because it's not the status we want for this instruction. And then we use the trick, the PDP-11 trick of auto-incrementing on the program counter to read the branch offset from the next cell in the program. So it's in line with the micro instructions. We logical AND that inline offset with W, which means it can be the result can be one of 2 things. It can either be the inline branch offset because W was all 1s, or 0 because W was all 0s. And finally, we add that value, whether it's an offset or 0, to the program counter. Drawing here. And a branch of 0, which means no branch, continue the program right where you left off, or it would, with the correctly calculated offset, take you to a new address. So that was the amusement. I heard some laughs in the audience when I mentioned that last month. So I had to bring it in more detail. I'm not going to bring it into this much more detail. This is the same logic, but not applied to machine code. It's applied to the 4th interpreter and the thread. The main difference is we're now applying a 0 or a branch offset to the interpreter pointer IP rather than the machine's program counter PC. The other question I said I'd come back to was alternatives, because the 74-172 is impossible to obtain. I first looked at the 74LS670, which is a 4-word by 4-bit register file. Problems with that are there's only 2 ports. One's a write port, one's a read port. More importantly, it uses a transparent latch instead of being edge triggered. The 172 does not clock a new value into the register until the very end of the execution cycle, and it gets the edge of that clock is what loads new data into 74-172, and this is necessary for all those auto increment functions. We want to read the value of A, and when the instruction is finished, update the value of A. With a transparent latch, back up 1, back up 3. If you can see that sort of red loop on the address bus, the A bus, if that were a transparent latch in the register file, the moment you output to the B register and it got circled around back to top to the ALU, and then through the ALU and back to the A input on the register file, you would basically wind up with a big clock generator. The thing would start oscillating between the states because there is no protection. The moment you put a value on the A input, it goes out on the B output. So that is the biggest stumbling block, there we go, on the 670. Also, it has its own restriction that you cannot read and write the same register simultaneously. So probably plentifully available, but not really useful for the PISC. There's a 74 ALS 870, which is a strange chip. It claims to have 2 16-word register files by 4-bit wide. I don't know why that's the same from one 32-bit register file, but that's what it's got. Again, only has 2 ports, but either port can be a write port or a read port. It seems to use, I've been puzzling through the documentation, it seems to use a transparent latch, so that same problem with the 670. And frankly, I don't know if 870s are available. I think it may be as rare as the 74-172. I was going to leave it at that and say, well, sorry, I haven't got an alternative, but you guys are going to be the death of me because at 3 in the morning, I woke up just, what would that be, 6 hours ago? And realized that wait a minute, thinking of this from the C register end, the memory data register, that's it. The memory data register is always a single register. It doesn't have to access all 8 registers. And in theory, a simple 74LS374 could be a memory data register. Now, I only thought of this 5 hours ago. It woke me up out of a sound sleep. So I don't have an answer yet. Would that work? But that's the line I'm investigating right now. And I hate to say this yet again, but I'll have to get back to you on this one. The other alternative that was being requested was the alternative arithmetic logic unit. The obvious candidate is the 381 and 382 74LS family, which are advanced ALUs, but not so far. They're old enough that they're still available in quantities. The problem is that only has 8 ALU functions, which arguably are the most useful ALU functions, you know, B minus A minus B, 3 logic functions. But it doesn't have those weird functions that I use, like add 1 to a register or propagate a register, the carry bit throughout all the bits of a register. So I don't think the gain there is much, and I'm fairly sure 181s are still in reasonable supply. Second option, I saw something called a 74AS881, but it turns out that's essentially a 181 developed in AS technology and with a couple of other what they consider to be improvements. So that's no change. And then finally, this was not a 3 in the morning thing, but it occurred to me a few weeks ago that, well, the AM2901, which I've never actually built with, is a combination of an ALU and a register file designed to go into a bit slice microprogram machine. May or may not be suited, depending on the choice of ALU functions. And the microprogram counter then is really not part of a general purpose register. The microprogram counter is separate, and on an AM2901 computer is provided by a different chip. So I'll have to see if I can work around that. So I don't know that that adds anything, but I think the problem of the not so significant. The final, I'll get back to you from last episode, was on the microassembler and the simulator. I had a microassembler working for the PISC, and you've seen samples of it when I show any PISC code. That is lost. It is somewhere in the last 30 years when I moved from one computer to another, I neglected to copy those files. And so there's a reason this page is mostly blank. Now, I have nothing to report on the microassembler. I've started working on a draft of a new one based upon the fragments of the assembler syntax that survive in those µEforth listings, or µEforth examples. And I've done no progress on the simulator in the last 2 months either. I actually started writing the simulator about 3 months ago and got sidetracked. What can I say? So that's the I'll get back to yous that I had promised last month. I'll move out of the way again and turn the video back on so you can see the machine. Are there any questions? Stop sharing.
No, doesn't seem to be the case.
Start video. It doesn't seem to be wanting to take my video again. How odd. Oh, sorry, I can't put the video back on. I guess I can probably put the screen back on. Why is this not letting me turn the video on? Oh, very odd. And Ulrich, your image is completely frozen on my machine.
Yeah. Hands up.
That's probably my end. I've got your sound.
Okay. So we don't see your video as well, and it still shows as the camera is switched off.
Yeah, and it won't let me switch it on. I click on start video and it does nothing.
Yeah. Well, what we could do is that you disconnect and reconnect the conference, but maybe first we can discuss some stuff. Are there any questions to Brad? So what are your plans? So you want to restore the system, and do you want to make it somehow available, the plans, so that people can build it on their side as well, or what
Well,
is
let me
your
first
future?
see. I'm completely frozen here. I can't even do chat. I'm going to leave and come back. I'll come back
Okay,
shortly.
do that.
Hello. It won't let me leave.
Well, I
to close the web
I can
page.
try it. Yeah. Okay. See you.
Okay, I'm gonna have
It's
to
the
restart
matrix.
the web. This is the matrix. Yes.
Yeah. A glitch there. So he's still there. Anyway, so yeah, it would be an interesting exercise to build a system like that, and so to have this minimal capabilities, like the things that we had in the µEforth system as well. So not really a CPU or CPU from discrete parts. So that's probably very interesting. And still it runs force, so that's great. Hello, Don. And yeah. So we're currently in the situation that Brad was with us, and somehow on his side the system froze, and so he's about to reconnect, but I still see his name in the list. So even disconnecting doesn't seem to work. And I don't know if
just pull the plug on the PC. Well,
well, I have an option like remove, but I don't know what implication this actually has. Whether he can reconnect afterwards. Sometimes Zoom is designed like for a class of pupils, and if you have someone who disturbs the class, then you want to throw him out and not allow him to get back.
and
It
this
could be
is
something
Zoom.
like this.
I got some problems with Zoom when I was presenting, and I wanted to share a different screen window, and I didn't get that done. That was frustrating. But anyway, this TTL CPU seems to be a lot simpler than Talos ES that Bernardo is developing. And it can actually run forward. And this thing that Bernardo is developing, this Talos ES, it can do parallel instructions somehow, but it's only in a very limited setting, and I find it a big challenge to get forth done on it. I hope I can get forth done on it. It's a challenge to me to get that done, to tame that system.
Okay, so yeah, let's see how do we intend to proceed. Shall we wait until Brad is able to reconnect, or shall we go with the next speaker and then let Brad, once he returned, to do his finish, or
It's
Peter, what do you think?
Ulrich, I think.
Fun?
Better we move on.
Yeah, I think so. Yeah, and eventually we will learn that Brad returns, but maybe the problems we saw are issues on his side, and he need to resolve them anyways. So yeah, with knowing that Brad will probably come in and will finish his talk, I would say the next speaker will be Virgil and talking about DUSK-OS. If that's fine. So Peter, you share the screen to show the schedule, but Virgil, you talked about your operating system approaches earlier. So, and today DUSK-OS, ForceOS with integrated C compiler, part 3. And yeah, we're happy to hear what you have to report in addition. if you want to, you can go ahead.
Yes. So hello, this is my third presentation of DUSK-OS. Previously, I've shown you the immediate mechanics, how STC, how DUSK was a STC, and then I showed you binary with modulators and then field. And today, I'd like to introduce you to the HAL, the harmonized assembly layer. So what is this? It's the foundation of everything I've shown you before, which is, you know, fancy code generation things. Well, it's built on the HAL. What it is it's a simple it's a layer put upon assemblers that has an harmonized API, so that you can write in the HAL in a cross CPU manner. So of course it's not an innovative idea, because as soon as you write assembler for more than one CPU, this is the first idea that pops up in your mind. But the thing is, generally it leads to a full-fledged programming language rather than an assembler, because CPUs have different capabilities. But in Forth, when you count on the fact that you can mix your assembler with Forth, then you can afford to go the simpler way. So you can shrink your specification and stay in the assembler type of complexity. So so that's a HAL, and it's designed to be mixed with Forth. You wouldn't want to write the whole program or OS in the HAL, but when you have a Forth with you, then it's all fine. So I'm going to show this to you. So I will stop my camera and share my screen. Where is it? Here. So do you all see my QEMU screen? Do you see?
Yes, we see it.
Yes, we see the share
Yes.
So so this is the same thing as last time. This is a i386 virtual machine running under QEMU. So this is DUSK-OS in bare metal mode. So first let's load an assembler, and the disassembler, and we'll use it right away. So i386. All right, so we have an assembler and disassembler loaded. First, let's try something simple. For example, let's create a code that adds 42 to PS stop. So in assembler, in i386 assembler, if you remember, AX is PS stop, EAX is PS stop, ESI is PS pointer, and ESP is register, is the return stack pointer. So if we want to write a word that adds 42 to PS stop, then it would look like this. All right, in red. So this is the equivalent in, for example, if you use NASM syntax, this is an equivalent. All right. So this, of course, will work. So for example, if we add 42, we see that it works. So this is just regular assembler. Now in the HAL, it would look like this. So the HAL is always, I don't need to load anything, because the HAL is implemented by every kernel of DUSK. So so by loading the kernel here on my i386 machine, I have the HAL. So I do the same thing here. So so you see that this is pretty similar to regular assembler. Of course, it will work. And if we disassemble it, we see that it looks, it does what it's supposed to do. So And what we see here on my mouse pointer is the important part is the plus comma. So it means write an instructions that adds the 42 immediate to the work register. And in the HAL, every operator has the work register, which is PS stop, as its inherent, not inherent, but default destination register. So we never have to specify it, because as a default, we work on PS stop. So this is a general introduction to it. Let's have a look at its API. I'll describe it in more details. So wait. All right. So this is the API help. This is the API description. So I will skip past all this text, and I will go straight to the API part. So for example, these are all the operands that are possible when we write. For example, if we want to create an operator that works with an wait. I'm not describing this properly. So every HAL operator, such as plus write, has one operand, and the operand is the destination register. So for example, if I write W parent plus write, this means add the work register to the indirect work register, which is essentially a fetch. And there are 3 registers that are 5 registers that are available to the HAL. So there's the work register, which is W. There's the A register, which is a separate register that I call the address register. The S register, which is the scratch register, and PSP and RSP, which are the same as in µEforth. So we can all address them when we generate code. And there's also we can also address immediates and the hard-coded memory addresses. And to all of these, we can add an offset for indirect plus offset accesses. And then on top of that, we have small flags that we can set. For example, these three lines here. So these are modifiers for our operand to change the destination register, which, as I've told you before, it's the default destination is the work register, but it can be the address register or the scratch register if we want. So, have I told you before? Whenever we specify a source for our operand, it's always indirect by default. But if we want, we can address directly the register. So we do this with the ampersand, and this here, the 2 brackets here, the 2 angle brackets, are for inverting the direction of the operator. And finally, we have with flags, which allow any operation to be an 8-bit operation, 16-bit operation, or 32-bit operation, which is the default. So this is how we parameterize most of HAL words. And well, this is just too complex for this presentation, but we'll go to the the instruction part. There's a few of them. So there's fetch, there's store, there's swap, there's arithmetics, and there's of course AND, OR, and XOR. And then here there are special ones which are fetch plus and the minus fetch, and store plus and minus store. This allows easy push and pop. So this is a fetch with increment, or a fetch with post increment, or store or fetch with pre decrement. This allows easy push and pop using a particular register. There's of course compare, and there's a plus n means add a hard-coded number to whichever your source is. And minus w negates the word or the work register, which is useful in some situations. So these are the instructions. There aren't more of them, and we can. So it can be a bit complex. It's difficult to make sense of what I've just shown you, but it will be easier if I show you examples. These are, for example, actual words implemented in the HAL. For example, if we want to implement drop, this is PSP fetch plus. So PSP is a PS pointer. So this is a register which is by default indirect. So what this means here, what we have here, this means take the 32-bit value where PSP currently points, fetch it into the work register, and then afterwards increase PSP by the width of the operation that has just taken place, which is essential. Oh, wait. This, sorry, I was mixed up. This is the no, oh, sorry, I'm mixed up. So this is exactly what I've told you. So this is a drop, because the work register will then have the value of what was in PSP, and because PSP is increased, then it shrinks by 4. Sorry, I'm a bit confused here by my own code. So this is a drop. The dupe is the opposite. So we take PSP, and instead of doing a fetch plus, we do a pre-decrement and then store. So we take what is in the work register, we grow PS by 4, and then we store what was in the work register in PSP, which is a dupe. Swap is even easier, because all we do is that we swap the work register with where PSP is pointing. NIP, we've seen NIP already when I was talking about immediate mechanics. So this is the same thing. NIP is only the only thing that NIP does is shrinking PS by 4, and then over, and then L shift. And 1 plus is, of course, as I've shown you before, an increase of an immediate 1. So this is basically the HAL. And to give you a better idea of how it works, let's implement something a bit more substantial. For example, in DUSK, we have strings. A string in DUSK is a counted string. So for example, if I dump my string, we see that it begins with a count, and then the content follows. In DUSK, there's the word S-type. So if I take my string and then S-type, it will type it. So this is a word that already exists. But if we want to implement that word in HAL, then it's possible. And let's do it. So this is a native word. So we're compiling, we're generating code. First of all, so my S type here will have to call the word emit repeatedly. So because we do that, we need to begin with a word that is called push ret, because HAL is cross CPU, and so on the i386 this is an OOP, so push ret does nothing. But for example, if you want to write my S type for if you wanted to work on ARM, you need this, because on ARM you need to explicitly push your LR register into the stack. Otherwise, you're losing your return address. So this is a cross CPU API that needs, so it needs to be called to have a my S type that works on all supported CPUs. Then what we want to do is to keep a copy of the address of string somewhere better than the work register, because we'll work with it. We'll use the work register for something else. So this is essentially copying the work register directly into the A register. If I didn't have the ampersand thing, it would store the work register into where A was pointing, which is an undefined place at this point, because we don't know, the A register currently has no value, undefined value. So at this point, the A register has the string, as the address of the string. Then what we'll do is that we will do an 8-bit fetch of wherever A is pointing to, and with a fetch plus. So what this will do is that this will put the first character of the string into the work register, and then increase A by 1. So at this point, the work register has 5 in it, if we call it with my string, and A points to the first H of the string. Then we can begin the loop. So begin is the same as with Fort. It just pushes here to PS. And so now we're in our loop. So what we'll do in our loop is that we will repeatedly fetch whatever A is pointing to, and we will call emit with it. So to call emit with it, we need some breathing space on PS. So I am compiling a dupe, which is essentially the same as what I've shown you before, but I find that reusing the dupe compiler makes the code easier to read. So I use this. So now we have reading space for emit, and then we do again an 8-bit fetch on the A register. So this does the same thing as we did before, but instead of fetching the length, then we fetch the character, and the length stays in the value that we've just duped. So it's in PS and at the second position of PS. So oh sorry, now we have a problem because I haven't written the thing. I hope it will work. The dupe has been written, but not the other instruction. I hope it will work. Here. Fetch plus. I think it will work. So at this point, the work register has H in it, well, whatever character, because we're in a loop. So now we are ready to call emit. But because we're calling a fourth word, we're going to lose the value of A, because the A register isn't preserved by fourth word. It's preserved by HAL words and macros, but not fourth word. So we need to preserve A. So we'll push it to RSP. So what this does here is that it's a push. So as I've shown you before, the minus store is a push, and the fetch plus is a pop. So here I'm pushing the value of A. Because A is a destination of this operand, I push the value of A into the RS stack, into the return stack. So now I can call init. So this is the address of init, and then branch R I'm compiling a call here. And now that after I've compiled my call, then I can pop back whatever I've pushed before. All right, so this is a call. So those 3 lines are a call to branch to emit while preserving the A register using the return stack. Now at this point, emit has consumed whatever was in my work register. So at this point, my work register has the count. So what I'm going to do here is that I'm going to decrease the count by 1. So 1 immediate minus right. So what this does is it decreases the work register by 1, and this operation, as is documented in the doc-hal.txt, it sets the Z flag in HAL's API. So right after a sub like this, I can use a conditional branch directly. So a conditional branch is branch C. So what I did there is that I specified the condition, so which is NZ. So branch if the Z flag is not set, and the branch C takes an address parameter which has been given by begin before. So this is our loop. This is what closes our loop, and then branch C takes an address and spits an address too, because those in HAL branch operations can be used for both forward branching and backward branching. So if I wanted to do a forward branch, then I would use what I'm just dropping there, but because this is a backward branch, then I drop this because I don't need it. So right now, I don't believe it. What? Oh, this is my begin. Oh, I'm so sorry. I messed it up. I can't type. Oh no. I messed it up, and I will not be able to show you how it works because I will not type this again. Will I type this again? I don't think I will type this again. Should I? No, this will be boring. But if you want to try this at home, what I've wrote there will work. It's just because I lost my begin earlier, and this is all messed up. Oh. So if this was going to work, if you want to try this at home, this would end with writing a drop, because at the end we have a 0. If the branch C doesn't branch backward, then it means that W is 0 and we're done. But we need to drop our W so that we obey our signature, which is to take a string and drop it. And we end with popret so that our word works with ARM, and then we exit. So if I hadn't messed up with my earlier A parent 8B fetch plus here, this word that I've just typed would work, and we could use MyStype in the same way that S-type works, and this would be happy. But then I'm very unhappy that I messed up my presentation. But this is supposed to work. Now, I'm going to take my senses back because I am confused. But so if it had worked, then you'd be pleasantly surprised and impressed. And then I would show you one other attribute of the HAL is that this is implemented directly in the kernel. So for example, if we open the kernel, okay, so this is the code for the i386 kernel, and then if I skip to the implementation of the plus store, so this is the implementation of the plus write that I've used before, and so this is what is mind-bending about the HAL. The thing is that the HAL could be used on top of the fourth assembler. This would be quite simple because it's only an harmonized API over whatever the assembler is generating. But the thing is that what I've shown you in previous presentations is the core of DUSK, and at this point we can't have an assembler available because we're booting, we're writing whatever we need, such as the two words, the fields. This is all foundational to DUSK, and the assembler needs those mechanics to be compiled. So for the HAL to be used in DUSK, it needs to be implemented in the kernel, in assembler itself. So this is the mind-bending part of HAL. So this is what you're looking at right now is DUSK dialect of i386 assembler, which assembles a word that assembles an addition in i386. So this is not an i386. This is not an i386 addition. This is an i386 addition assembler. So this is one meta level over. And in DUSK, what is crazy is that in DUSK, this is not a fourth kernel. This is a fourth kernel assembler, because in this file here, we don't have drop, we don't have over, we don't have rot, we don't have plus, we don't have div mod. All we have are assembler words. The actual fourth kernel is implemented in fourth. So for example, if I quit this, so when the kernel boots, it has almost nothing, and then it reads this file. So as soon as the first instruction that the PC booting the DUSK-OS kernel is running, it runs this from memory. Okay, the C here is the very first character that is read after boot, and at this point we have nothing. So we don't have dupe, we don't have drop, we have nothing. So we bootstrap ourselves, and then we. So this is very bootstrappy, and then only later, for example, we can implement drop. So no, drop has been implemented a little earlier, but let's use swap. Okay, so we have no swap, compiler. This is where swap is implemented in DUSK, but this is not binary. binary code. So this is, for example, swap is implemented in the very same way in DUSK ARM as in DUSK i386. This is the same line that implements the swap compiler and then the swap. So it's the HAL that allows this. And this is what makes the HAL really mind-bending and crazy and really powerful.
Virgil,
yes?
we have 2 minutes more, and then we go to the questions and answer.
Yes, I'm finished. I would just wanted to show how the DUSK-OS bootstraps itself, and I'm pretty much finished here.
Okay, thank you very much. Thanks
right.
for your talk. I have 2 questions, but maybe there are other questions as well. So please go ahead and ask, Virgil.
Is my screen? All right, wait.
There you
So
are.
first of all, sorry about the mess. There's really nothing I could do. There was a mistake in my typing, and then I couldn't show it working.
We go
but
to the
I assure you it works.
Let me do some questions, Virgil.
Yes.
Somebody else has questions for Virgil?
Sure. Me too.
Okay,
Anyway,
then
I wanted to say,
oh,
I wanted to say that's fantastic.
Thanks.
Right. So maybe I ask one question and then someone else, and I have another one. So my first question is, what we saw is that there is no precompiled binary apart from the small kernel, and then you assemble and you compile the entire system on the fly while booting. Is that right?
Exactly. And this is what makes Dusk special. Yes.
Is this where the name comes from? So it boots from Dusk?
Oh no,
the
Dusk. No, the name doesn't come from there, but
yeah. Anyway,
can be seen as some kind of allegory.
Yeah. Peter, do you have a question?
Okay. Then we move on.
No, I have another
for
question.
me.
I have
Then
another question.
another one.
Okay. We saw you're using code to define code words using HEL, and that's great. Do you have code and headers separated, or do they intermix?
Code and header.
Yeah. If you say code my S type, then the header has to be stored somewhere. Is this also at the same place where the XML?
That's what is really great about STC, is that there's no header. So the code word just creates an entry.
Yeah.
And there's nothing, because you jump to that entry and it's
but
binary.
How do you handle the symbol table? I mean, you use the word my S code, my S type later on, or you intended to use it later on. So there's some kind of dictionary lookup. You enter words and they are looked up. So
yes,
how
it creates a dictionary entry. The code word creates a dictionary entry in the
and
fourth
my question is the code interleaved with the dictionary entries like in a traditional FigForce system or
Yes.
F83?
Yes.
Or is it separated like in ColorForce, which has significant advantages?
No, it's not separated. I've never considered the question.
Yeah. Well, then the nice thing is the symbols could just be entry points in a huge long stream of assembly code. And you can do fall through, for example, fall from one definition into the next one, and things like this, or jump in between definitions very easily. So that's
well, I'd have to consider it. I've to look it up. I've never considered.
So yeah, just thank you very much. So I can think about that.
Rich, a comment. A comment for Rich. When we get into the fourth cafe afterwards, can we have a discussion on this separate headers? That's very interesting to me.
Yeah, sure.
Well, I'm a little short on time, so after my presentation, I will have to go. So I won't be able to be present, but I'd like to chat about this at another time. But today I won't be able to.
Sure. Yep. Then the next time. I think now we're done. So, which means our next speaker. will be Pablo Reda. And oh, Peter is sharing the screen, so we can see the schedule. Pablo will talk about game development with Force. And I know this is quite exciting and good for the eye. And so, Pablo, are you with us? And could you, or do we do Brad's finish first?
Oh yeah, we had questions for Brad because his video was stopped suddenly. And if there are any questions for the first presentation of Brad Rodriguez.
Yeah.
Last call, presentation, Brad Rodriguez, any questions?
Brad, in principle, you could try again using the camera and showing us the board, or what I think you wanted to show the board.
Well, I'll try. Is video coming through?
Yes.
Yes.
There we go. I have to move someone out of the way. It's getting a little crowded here down in PISC headquarters. Video monitor, which I'm sorry you can't read, the TTL prototype, wire wrap prototype, and this green card on the end is the video card. It's a long story behind the video card, but it was built from a kit many years ago. And are there any questions? And do I need to bring slides back up? Hello.
Does it look like this?
Okay. Well, I was at the last part, the very last page of my talk, so I finished the formal presentation. The only thing I didn't do earlier was the question and answer.
Mm-hmm. So, are there any questions? The Brad, according to the CPU design. So I think my question was, how are your future plans? Do you want to complete and gather everything and then publish this so that people can rebuild it?
That's my intention at the present time, yes.
Mm-hmm.
I'm going to put some more work into it. Like I said, the simulator and the assembler are the next things that need doing. And I'm hoping to find some of my old code examples. But yeah, eventually I'll update the hardware design with a more accessible part and make that available.
Yeah, so we're looking forward to that. Great.
No, thanks again, and sorry for all the video problems.
Mm-hmm.
Brad,
sorry,
it
go
was
ahead.
an excellent presentation.
Thank you very much.
Thank you so
Thank
much.
you.
Thank you so much.
And now we go to Pablo. Thanks for your patience. Pablo, the stage is yours.
Thank you. Hello to all. I share my screen.
We see that.
Okay. I teach programming and informatics in a medium school. And with the student entering a game jam, this is the game jam, and make a 3 game for this competition. These 3 games, and I would like to show you some internal about this game and how deploy this game to enter the contest. This is my main development environment. I have the browser and the launch of 4R3 code, and I prefer edit the code in an external editor. I have this folder in in para, estoy, sorry. And this is the folder of the game of the game. The game. This is the game with the credits. And how play this game. This is how lost. And return to the main window. This game is compiled to bytecoders and executed for a virtual machine, the 4R3, and I would like to show how the animation system is made. The code of the game is here with load image, sound, true type found, and this is the main screen with the buttons for play and exit and the animated logo. This is this screen, and this is the code. Créditos, jugar, and salir, the Spanish word for credits, play, and exit. And the logo is an image in the folder. This is the logo. And this is the word who put in the screen the logo. The logo is loaded in a variable spare logo, load here. And in this case, this is the X and Y coordinate. I make this static commenting the variable and put literal in the position and save. And now the logo is fixed. Or I can use the mouse position for print the logo, and now the mouse position make the position of the logo. Then how I make animation in this screen? I add two variables. These two variables are here. In 4R3, the variable like color 4 are defined with another type of prefix, and this is a static position for the graphic. But I developed an automatic animation of values of the variable with this word. If I comment this word, now the logo or the graphic is still. And how work this? I reset this variable animation words, and this make an animation from from the time 0 with a length 1 second, with the type of animation 29 from the value -10 to 10, and modify the variable ilogo. Ilogo is this variable, and because this variable is used to choose the position of the graphic, this make the animation. Then I only the E variable. And if make decomment the other animation of the E variable, now I have the go and back, the for and back of the value of the value. This animation can be variable by a penner function, EASE function, call it. I guess this EASE function are this, and I can choose the type of animation of the modification of the variable over time. For example, I use to the E variable of the logo, 29 and 28 are bounce in and bounce out. It's a bouncing movement. I can change, for example, to L22 and 23 and produce this kind of movement. Then 22, 23, and 23 and 22 type of movement. And I play again, and now the animation of the variable is different from the other type. Well, this is one thing, how animate a variable without effort, because only I need define the variables for use in the put the graphic in the screen, and be update make the work of change the value of the variable. Well, and now with the two variables in the same times with movement. The other things I like to show you is how deploy this game. This game is compiled and executed by the 403 virtual machine. Then for not copy all the distribution, I use a conversion to this code to a form with all the libraries in one file, and with this I not need distribute all the R3, and this is made with plain code. Plain code make in the folder of source code, plain code, make this file, and this file is first put all the includes in one file. This is the same code, but in one file. and the name of words are replaced with word one, word two, and so on, and so on, and so on, and remove all the original names of the word. And with this, only need the interpreter and put this plain code called main for automatic call, and I can deploy this file, of course, with the files needed for the graphics and music and so on, in the same place, because in the source go to the same path to get the graphics, and then I can deploy this file, this folder with all of need for execute this game. This is one form for deploy the system. The compiler to bytecodes and the virtual machine still exist, but the source code is reduced to one file. No need library, external library of R3. And the other type of deployed a system is really compiling the code. Then I have the R3. I have a folder with assembler things. This is the flat assembler and a basic framework for compile the compile the program, and in the editor I can compile and generate in this folder all the code in assembler. I can hit F5. Then I generate the code of the program. In the code of the program is a static analysis of the program. Here, what happened with the stack, and some minor optimization and Intel 64 assembly about the code right in the source code. For example, over or shift for to left, and here occur an optimization because without this optimization need load the 4 in the stack and then make the shift and so on and so on, and last word are the call and the jump to the main words. And this assembler, this is code of the program, and this is date of the program with all the strings and all the variables who need the code for execute, and the executable generated here not work because need the reference due to the graphic in the exact folder who look at the sound and graphics. but I can translate to the folder prepared for this here, and I don't need a virtual machine or source code, and here is the here's the working code. And this all. If have any question?
Thank you very much. Again, I have questions, but maybe others want to ask questions as well. So please go ahead, ask Pablo.
I would like to have a teacher like Pablo when I was young.
Yeah, that's really great. So Pablo, my question was, who is doing the artwork? So if I'm programming a game, it looks really boring because I just use the standard fonts and whatever, and line drawing, and so. But these have so lovely cartoons, and also the letters are so well designed. So even looking at the presentation screen, you immediately get the idea. I want to play that game. So who's doing the artwork?
This is a part of the work with the students. Not all the students go to programming, and some make sound, some make it graphics, and
wow.
In the class they are a graphic artist with me. I do the computer things, and she, the graphic artist, do the teach the graphic things and make this thing. I am not doing graphics too.
So this is an interdisciplinary class with children of different capabilities, and they learn how to split work, so that everyone is doing what he's best at, and then they bring together to make a whole product. That's amazing.
Yes.
That's amazing.
Yes.
Yeah.
Pablo, is there any way you can present this in a Congress of Education so other teachers in the computer area can watch your work and probably teach R3 graphics and programming in other states?
I am slowly advancing in writing manuals for now in Spanish, but try to document this work. But I am slowly making or trying to make a very complete for a student with no knowing of programming. This is my goal. Using FORTH to teach programming, because the simplification of FORTH in 4L3 and so on.
Yeah, that's great. So the development system that we saw, you had the R3 source code edited in Notepad++, is that right? And whenever you did some keystrokes, the compiler ran in the background. So the changes that you made were immediately available in the running program.
Yes. I don't add to the internal editor the copy and paste capabilities, and is very convenient use copy and paste, and it's more easy add use Notepad++.
Yeah. So how did you convince the editor to do colors in the way you use it?
Yes. I edit the colors of the words. It's very easy, but the colors of R3 depend of the prefix of the word, like color FORTH. And and I not can change the color of the single quote words because is taking like a string, and well, I have a difficult, but because in 403 the single quote prefix is the address of the word, a variable or a executor or a code, data or code.
Yeah, so what we see is actually syntax highlighting. So depending on the token and the prefix, it displays, if it has a colon in front, it's displayed in red. But it's inspired by the ColorForce colors.
Yes, in the distribution is this file too. If download the distribution, this is a XML file to send to Notepad++, and you have a full color.
I see, great. Yeah, excellent. That's quite good. So are there other questions for Pablo? I mean, this is really exciting. Having having this animation, you have variables and you say, please animate over time the variables, and then you use the variable in your program, and whoops, you have the animation on the screen. I mean, that's really great, and try to do that in some other language in the interactive way that we just saw. This is really mind-blowing. It's a kind of directness that is really, really amazing. And yeah, so that is quite great. Yeah, indeed.
Thank you, Ulrich.
Sure. Any other questions? Well, Peter shows the schedule again.
If there are no more questions, then we move on to the next presentation, which is Ulrich Hoffmann, exchanging force programs, ideas, packages, modules, and many more.
And the web. Yeah.
On the web. On the web.
Yeah. So let's see. Right. So I share my screen, and then we will see how things will work. Yeah, here we are. That is great. And I have a small screen, so I now have the Zoom controls on there. Yeah, so I try to write force programs that I can give to others and make them use in their system. And I faced the issue that how should I actually package these programs? I can publish them on some website, and you get the source code, you load it into your system, but then I use words that are intended to be useful, to use the package, and then there are other words that are just used internally to realize what I want to show. And actually it turns out that there is no good way to package these things. They are different, and again, if you've seen µEforth, you've seen µEforth. There are different approaches to actually do that. And I want to talk a little bit about how to package software in a way that you can just load it in your system and then have available the commands that are intended for further use. So, and we do approach this the following way. I will give a short introduction, which I'm currently doing. We look at the classical things. How do you deal with the situation that you have internal words that might collide with the definitions in other packages, in other applications? And the traditional thing to do that is vocabularies, and the 94 standard has word lists to accomplish the same thing, and lots of people played around with this switching of word lists. You can call them namespaces or whatever. And if you look at commercial systems, but also in GeForce or in Win32 Force, then you will find one or the other way to package things. So VFX has so-called modules. We will look at this, and then SwiftForce has something that is called packages, and neither system has the other stuff. So which is difficult to if you want to write a program that is supposed to load on this system and also on this system and on the third system, if they don't provide the appropriate words, then you immediately stuck. You load something and it says module question mark, or it says package question mark. Yeah, also in FoxForce we had an approach which is the vertical bar, which was, I think, it originates from the in the Polyforce meta-compiler, and I will show you about that. So currently what I'm doing, I'm writing phrases like word list, get current, and get order, and then some stack manipulation set orders, like 3 lines at the top of my programs to manage a namespace or word list in a certain way, so I can put the private words in there, and then on the fly use the words to manipulate the word order to define public words, and back and forth. And I really dislike this, but it's the only way that I can load this on BFX, on SwiftForce, on GForce, in Win32Force, and other force systems that work. And I really would like to have some common understanding of how we create packages. So, and then the second question is, how do we publish packages once we created them? And that's my second talk, or part of the talk. We will look again at Project ForceWorks. And there's also the Force.net. Project ForceWorks for exchanging ideas, and the Force.net for actually distributing packages. So they are not fighting against each other, but they augment each other and complement what to do. So yeah, so that's the idea. We share ideas, and this is what we do. And I'm amazed about the talks that we heard today. Lots of ideas and so little time to follow up on that. But I appreciate the HAL, the HAL layer, for some common assembly language that might be low level but still portable. So that's all great. So we do exchange of ideas here in the Force 2020 group. Yeah, and I also want to change programs, and probably others want to change programs as well. So Francois published his SHA algorithm, and certainly he wants to others to make use them and pick it up and use them on their system as well. So we want to package programs, and we have some internal words and we have external words. Internal words that are only used for realization. Of course, there might be interesting factors that you might want to use, but it's a very hard thing to only provide great factors of words. So typically you define something like an interface. So this is the collection of words I want to provide and that you want to use. So, and currently there is no good way to distinguish between these internal and external words. Yeah, so what you need to do is you have your program, you need to package it, and then you need to distribute it at some platform, be it the Force.net or Project ForceWorks. So classically, yeah, we use vocabularies and word lists, and or word lists. Some systems provide both, some provide one, and some the other. To manage namespaces, so we can define words with the same name in different contexts. Yeah, and the classical thing is the assembler. We also saw about the strange commas at the end of assembler mnemonics, which are to compile. That's one way you make the names distinct. Yes, then you have and in Force and comma in the assembler. But if you don't want to do that, then you have to distinguish between and or in Force, which work on the stack, and or in the assembler, which work on the registers of your processor. Or you have the Force word I, which is the loop index, and inside a command-driven editor, you have the command I for insert a string. So, and this is the reason why vocabularies came into place. So many systems that don't need this even don't provide vocabularies or namespaces or word lists. Yeah. So, but if you have them, then you can have words with the same name that have a different meaning. And to access them, you have to manipulate the order in which these word lists or vocabularies are searched. Yeah. And yeah, if you want to provide something, maybe you create some new vocabularies to define new words in there. So using vocabulary and word lists at the low level as they are standardized is quite difficult to do, and you have to be very careful what you do. Typically use established phrases that work fine because actually you don't know in which state the system is when you load your source code, so you have to be very careful not to disturb anything that is going on there in the first place. So there are high-level definitions in systems that deal with this, module export and module being one of this. So you could, in µEforth, for example, you could use module, you give it a name, and then you can define internal definitions like hello and mods and hi. And then you export the word that you want to use. These are visible outside of the module. Yeah. If you use the module, you get only the exported words to use. If you want to dig in, there are capabilities to do so. So if you load that module as defined here, then the word hi is available outside, but hello is not accessible. You get something hello is not found or whatever happens there. So you can distinguish between internal words hello and mods and external words hi in this case. Well, that is Stephen Peck's invention. µEforth has it, but I don't know of any other force that has it. So actually, if you want to write a portable program, you can't use module export and module because, well, it only loads on µEforth. So we can have a look at the other vendor. They do package, private, public, and package. Well, it's more or less the same. You only have private sections for the internal words, and you have public sections for the external words. And it's more or less the same in green, but different words incompatible with the other approach. So you do this, and again, hi is the external word, it can be used, and hello is internal, cannot be used. µEforth, for example, has an approach where they have a single vocabulary called inside, and all the internal words go inside that inside vocabulary. So if you want to have something inside, you say inside definitions, and if you want to have something external, you say forth definitions. You could think of, well, why do we do this at all? Why do we want to have private words, internal words? But if you've seen one of a system where you loaded several packages, then there is an overload of words. If you do words there, a huge amount of words, and you can't really figure out which are the words I intend to use and which are just internal words for implementation. So I really think this is something that we need. In µEforth, we had this bar, the vertical bar in front of internal words. And in Polyforth, in the meta compiler, this was also used for defining words that didn't get a header in the resulting image. And in µEforth, you can use it just in the normal forth system. You put a bar in front, marking a word as being an internal word. And then the header is still created, but it's marked as being temporary. And as long as you continue to work, you can access the word hello and bar in this case. You can define words like hi in this case using hello and bar. But if you use the word clear, then all temporarily marked headers are removed from the system. So all the internal words disappear, and we have the same effect. Hi is still there. It calls the now unnamed words hello and bar. And hello is no longer accessible. The code still exists, but the header has been deleted from the system. So that is quite nice to work like this. So you mark the internal words, those that you consider to be only relevant for the implementation and not for further use. So yeah, that's it. Once you have created and packaged your thing, then you should talk about that. It's always good. Do good things and talk about that. And so there is Project ThoughtWorks, which is hosted by Forstgesellschaft Wiki, so which explains this strange URL to access it, but it's available in the slides and we can put it in the chat. It's a collection of ideas. So with Project ThoughtWorks, we said, well, we accept that there are different force systems that are not compatible. So the common thing is, well, you challenge an idea, you want to know about some technology, and you can share the approaches how to deal with that technology, be it communication, be it some algorithms, being random number generation or whatever. And so you describe the problem, you could describe the idea, how to approach things, and eventually you also present some source code, how to solve this in FOSS, but all dialects are welcome. You can you just state this is for system XYZ, and then it could be system specific, it could be non-standard or whatever. That's all appreciated. And by looking at the source code, you can learn it. If it happens that your system is under those that provide implementations, you can just pick it and use it. So that's one way to exchange ideas. And that's what the Project ThoughtWorks is about. And we are welcome you to also share your ideas, to write about things that you want to contribute to the community. It's all publicly available to see things. If you have some package where you say, well, that's something I really want to contribute, so that you can download it as a zip file and unload it at your specific system to make use of it, then there is the force.net. And you can use the force.net to actually have a look, and we can have a look at the force.net. And there is actually the way to look at the packages that you want to have, and it's not too difficult to provide packages on your own here. So it's not necessary to just keep a couple of people to do that. And for example, we can look at dynamic memory allocation that implements allocate free and resize for systems that don't have the standard word set for memory. And so it describes how to use the package. You can browse the source code. You can read Klaus' original paper on the formal 88 conference, and you can download the zip file, unzip it at your location, and then make use of it. So it's actually, yeah, and there you of course you need to read. This is actually FOSS 94 standard code. So if you have a system, then you can use it immediately, or if you have a FOSS 2012 system. But if you have a different system, well, you might need to have some adaptations. Yeah, it uses common force, nothing really special. And as you can think, well, the words that you are supposed to use is allocate free, resize, empty memory, and size, maybe to find out how large a block is that you allocated. But there are lots of internal words that are not relevant for using this. Yeah, and you can click on the glossary, and there you get the documentation of the external words. If you're curious, you can look at the source code, and you see there are lots of different inside word like fits question mark or whatever. This is not packaged in the way that I described, because I actually don't know how I should do that. And so that's mainly the focus of my talk. Yeah, so to come to a conclusion is I think we want to share ideas, and this is why also FORCE 2020 exists. And that is also why we have the project ForceWorks to exchange ideas about technical things and talk about solutions and the background and pitfalls and whatever, and provide also for source code in many dialects. Yeah, we want to share source code, and yeah, you could just publish it and everyone just copies it and tweaks it as he wants to. But I also want to package code, source code, and describe the package and enable everyone to use it. So I need to also distribute it. So I need some way to describe the package, write the package, and the ForceNet is one way to actually publish it. Or you can just put things on GitHub, which is also fine. And people get it from there. Yeah, but the remaining question that I currently have is, how do we package it? Shall we use all modules? Shall we all use packages? Do we invent vertical bar for other systems? Or do we have something else? And yeah, the question is, can we agree on something where say, okay, let's vote on this, we all use packages? That would be fine with me. I don't see one way being better than the other way, but having no common way, that's a bad thing. And I hear in this group many times, whoa, we need libraries and then everything will be fine. So this is a real reason why we don't have libraries, because there is no way to actually write them in a way that you just load them in the system and get the words that are intended to be used. Yeah, and that's it. So I'm open for questions and maybe some short discussion on what we shall do here. Christian.
Really fantastic.
Okay, so I missed something right at the beginning. What's the meaning of internal and external in a few words?
In a few words, external words are the words that as someone who uses the package are supposed to use. And the internal words are only for realizing what you have. So if you think of the memory allocation word set, there are words inside, internal words, fits, question mark. And so you're not supposed to use them because in the future version, they might change or whatever. And you're supposed to use allocate and free and resize. So there is it's modular design. There is a distinction between the inside of a module and the outside of a module, the interface that you use. Yeah. So internal is the words.
All the Forth I used before didn't have any vocabulary.
Yeah. So okay. You are facing bloated word lists. I mean, vlist becomes or words becomes irrelevant if there are hundreds of words that you don't use or not supposed to use because they are not well factored or they are just dealing with some special inside things.
Yeah, I think there's something similar as a concept in µEforth.
Yeah. So maybe Travis can talk about that, what this is, and maybe we agree on.
Yeah, I can share my screen one moment and show how it is in FORCE 2020.
Yeah.
Okay, thank you.
Sure.
So this is the FORCE 2020, and it was former called ForceWin. This is a future development of the Russian SP Force, and we added a layer to make it compatible to Win32 Force. But this runs much faster than Win32 Force. It's almost 10 times faster, and we have modules since the beginning. I think that Stephen Peck took this from the Russian guys.
Okay, maybe it's similar to what I showed on modules in the VFX.
Yes, it's the same.
Yeah, so I know that the origin might be unclear. So both say, well, the other one got it from me.
So here you see
anyway.
Yes, it's just to not to blame anybody, but just to say that we have this, and I think the origins could be in Russia. I don't know.
Mm-hmm. Yeah, could very well be. So, okay, thank you, Pablo.
Yes, for contribute for your presentation. I know two system with different mechanisms. One is Peter Shakati. You use priv and pub. I think for public and private. And in my system, I use double colon and double hash for make the exported variable and word and simple for no exported.
Yeah. So essentially, you mark them also as being internal and external. Yeah. Okay, right. Interesting.
It's important because when you load a lot of code, you clog your dictionary with unnecessary things. And if you have libraries, this is very useful, very interesting. Force libraries like Ulrich showed us. It's really important to have these modules.
Yeah. So would you think it's interesting that also the standards committee will think about something and say, well, this is the way we say you could do these kinds of modules or packages?
Well, I saw you have Rubin. I can't remember his family, but it's Pinka.
Yeah. Right.
He can explain this perfectly. I think it's very important for the answer. For the answer, yes.
Yeah. So yeah, because currently I really have two or three lines of gibberish at the beginning, which is something like word list, dope, set content, or previously set current, and then get order or something to R. Or it's really a well thought out sequence, but it's a mess and it's difficult to understand anyways. So because we don't have words for doing what we want, we just have the basic.
We have a question from Joss, probably.
Joss, please.
Thank you. I would prefer a solution with old classic vocabularies, because that's for me an easy way to handle problems. And I also would like to say that if you mark words as hidden or internal, then you might regret it later because you would like to use it and you can't use it.
Yeah, that's right.
Well, I agree with Josh, of course, because we love to use vocabularies, force people, no? But I found interesting when you develop software for professionally and you want to deploy for a customer, the modules offer a layer of protection because the words that are not exported outside the module are not accessible by the user. He will never access the words. So if you have a software development which is in risk of human lives or in risk of using some hidden code, you don't want the user to have access, modules allow that. And vocabularies not. You have no protection.
You can use steel and you can't penetrate through it.
Yeah, so there are often ways around that, and you can deal with this with some discipline. Also in the chat is why don't you just document which are the words that are public words and others are internal words. Yeah, but it could be that I use the name of a word that exists in the system and I overwrite that word. Well, that works, but not if the original word is supposed to be used later on, for example. So there is a high potential of name clashes that can appear. So I really say, yeah, we need to have some way to hide definitions, make them, yeah, in some way second class. It's interesting to be able to access them in one way or the other. But to have reusable modules, I think that is really necessary. And as Peter said, it's not that you just use a single module, but you want to have the memory allocation words, that you want to have the string stack, you want to have the graphics package. And if they happen to have internal words that are the same, and you don't isolate them from each other, then you have dependencies on the load order, and or they don't work in combination. These are all things that we experience. So it's not that they just come out of fear. It's things that happened. And I think this is one of the reasons why we don't have libraries in the large scale. So where you can just go ahead and say, well, I need to have some string manipulation libraries. Well, I take this one and everyone is happy. That's not the case. We can't do that right now. And well, this is my idea of what is missing. And maybe if we have a way to distinguish between these interfaces and the internal words, implementation words, then this would enable us to really have libraries. And in the FOSS style, it's source code libraries. Yeah, it's not binary libraries that you link to your FOSS system or whatever, but it's source code libraries. And I believe that's great, because you can have a look inside and still have this sharing of ideas topic that you can follow. Anyway, additional questions or comments?
This is really interesting. So your data structures would be within the module.
Yeah, sure. Yeah. Okay, then thank you very much for listening, and thanks for the discussion. The schedule says, well, we are nearly in time, like 4 UTC, which is exactly 7 minutes ago. We are heading for a coffee break, which is great. I would appreciate that, of course. And then after the break, we can do some advertisement in between, of course. And after the break, Brad Nelson will talk about FPGA and Raspberry Pi Pico. Well, very exciting indeed. And so I would say we do some 15 minutes break. Is that fine? Or 10 minutes break? What, Peter, what do you think?
10 minutes is okay for everyone? Or
well,
do we need 15?
Yeah, so I think 10 minutes is fine then, and
Okay.
we meet 20 minutes past the hour, whatever the hour is at your side. So in 12 minutes, actually.
Should we pause the recording, no? Or
well, we can keep it. If you want to, we can stop the recording, then we are free to talk, and then afterwards we resume. Okay, so welcome back. I hope you all enjoyed your coffee. I will take mine soon. And I'm happy that Brad Nelson will talk about Raspberry Pi Pico and cool things, the ICE lattice FPGAs, and his effort on combining those. We know that µEforth is one thing that normally works as ESP32 force on ESP32 processors. So also this is exciting news that there's now an ARM port. And yeah, Brad, I'm so excited to hear what you will report. So please go ahead and let us all know.
All right. Well, thank you. I just had a scary little thing where I typed RMRF on a directory I did not mean to while trying to clean something up. So I'm a little bit jittery from that. But let me proceed and talk about the Pico-Ice. So. The background here is that Christopher Lazinski generously happened to gift me a Raspberry Pi Pico at 4th Day last November. To be honest, the Pi Pico and even the Raspberry and sorry, the Raspberry Pi Pico nor the Pico-Ice were honestly on my radar. But it gave me an opportunity to take a look at them, and it's quite an interesting system. It's got 4 megs of flash for the CPU and a separate 4 megs of flash for the FPGA. It's got an 8 megabyte SPI RAM. There's an LED, a couple of buttons, and most interestingly, it's got an ICE40 FPGA on the same board. And the FPGA is set up in such a way that the microcontroller can control it and can feed configuration to it, which is really kind of cool. I don't know if you can see it here, but it's also a tiny little board, really nice, plugs into USB. The CPU on it is the same one that's in the Raspberry Pi Pico. I now need to get myself one of those because I had not I had heard of them, but had sort of thought, oh, another board with ARM on it, and sort of didn't think more of it. But it's kind of a neat setup, and some interesting things about it. A good chunk of RAM. It's got a lot of GPIO pins, a bunch of UARTs. It's got a USB controller that is used to pretty interesting effect with the device. So when you plug it in, it's able to sort of produce a whole bunch of different virtual devices potentially. And so it's unlike devices that will plug in and sort of just have the serial port. It can spin up serial ports. It can spin up mass storage devices. So it's sort of at least the potential for over cleverness, but there's a lot there, and it can boot either off of the flash on the device or off of USB. The Pico-Ice, and what differentiates it from a Raspberry Pi Pico is that it has this ICE40, which is got 5K LUTs of FPGA on it. It's got a bunch of single-ported RAM, some dual-ported RAM interleaved with the FPGA. It's got a bunch of DSPs. This is sort of the layout of the FPGA, and it's got the DSPs are little multipliers. So there's eight of them, and they can do a variety of different size multiplies and multiply accumulates and so on. Well, that's the diagram of it. It's got a bunch of very configurable I/O pins where you can individually enable them for input output and let them float and so on, all under control of the whatever configuration you've got on the device. There's memory that's got dual ported interleaved within the thing, as I said before, and then a larger chunk of single ported RAM kind of on the rim of the chip. So programming the device is interesting. Unlike say ESP32, where we've kind of honed in on the Arduino tools, it's basically done with Git repos. There's a Git repo for the Pico SDK, and it can be pulled in as a submodule, and the Pico-Ice SDK in turn also pulls in a bunch of its dependencies as Git submodules. These can get a little bit big, but it means that you kind of can treat it as part of a project that you're managing in Git. And then to my surprise, a thing I had not encountered previously was that the way that you upload to the device is that it can pretend to be a flash drive, and you upload using this UF2 protocol. And then it, as I mentioned, it has a bunch of different, it can do virtual serial devices. This UF2 thing was completely new to me. I'm not quite sure the timeline and origin of it, but it's a neat idea. It's basically it's a file format that I guess Microsoft had come up with for some device or other, and it is structured around 512 byte blocks that are designed to be sort of atomically transferred over when mounted as a USB flash device, because that's sort of the unit of sector writes, and that way you know that they arrive in total or not, and each block sort of has enough information within it that it knows where it can be flashed. This makes it possible to write kind of an incomplete or part flash device driver on the device that looks like a drive, but essentially what it's there for is for you to copy in the thing to upload. So it's super convenient in terms of not even needing like a serial upload or specialized tooling. You just you've got a file you want to transfer to it, you drop it in this format, and it will flash it and it reboots. This is used on the Pico-Ice kind of in two layers. There's the default firmware with the Pico-Ice actually brings it up in a mode where it mounts a flash drive that is intended for you to upload a UF2 file for the contents of the FPGA, which is in turn actually a program that's running on the microcontroller that's doing this mode of operation. Whereas if you tie off one of the pins in the device, it will then come up in a mode where the bootloader for the microcontroller will accept something in the same format. So you can either program the flash for the FPGA this way, or for the microcontroller. So it's kind of a neat strategy for dealing with multiple devices on the same board. So porting µEforth, because the SDKs for this board are structured as submodules, I was able to add them to the µEforth repo as a submodule dependency. They're pretty heavily wedded to the CMake build system within this SDK. And unlike some of the SDKs, say like the Espertif one, where there's the assumption that you'll get a lot of it in the form of binaries and so on, this one, a lot of it is all sort of from source, and there's the assumption that you'll hook your dependencies into the chain of dependencies via CMake. I briefly contemplated working around that, but I decided that ultimately that was sort of seemed to be the preferred mode of operation with these boards. To bring up µEforth, I found that as I'd gone around for the different types of architectures supported and added fault handling, I had actually kind of heavily baked in some assumptions about fault handling typically being available, and so I ended up having to sort of temporarily shunt it out. I haven't yet looked into whether the setup with the Pico-Ice lets you do fault handling. My suspicion, given its ARM, is that it's possible. It's just a matter of finding the right way to hook it in. And then the porting process, I've kind of now got enough architectures for µEforth that it's starting to take shape to have a way to add in a new one. Basically, I have another directory for it, a separate main CPP that does some of the board-specific init, and then a built-ins.h with the bindings. I haven't yet made it flexible in the way that it is for ESP32, where you could pull in user words, but it uses the same system of macros and so on. One interesting quirk, I guess, about the UF2 aspect of the board is that in some ways it makes it more appealing than with, say, an ESP32 to distribute a built binary, because it's so easy for somebody to just copy it on. They get the board, they plug it in, they copy a file over to a flash drive, and then they're ready to go. But after I did all this, I compiled a little bit of fuss to get it to compile for the new target, but because it's being built in C, it at least built after I sorted things through, and then I fired it up and it didn't run. So what was going on? Well, it proved difficult to debug, and I think this is partially that I didn't dive very deeply into the tools on the for the RP 2040. But what occurred to me is that a common problem I've had when bootstrapping µEforth is that at some juncture I had pretty early on moved to making a lot of the IO words deferred. And so it's only a ways into the startup process that the IO words are actually mapped to anything. And so if you get any failures or errors early in the process, it's very easy to have it fall off the rails and just sort of silently fail. And so I probably need to figure out a better strategy for that in general, to sort of maybe default to some other mapping for those words earlier on. But regardless, I fell back on a strategy that I've used sort of for a related purpose with the ESP32, which is in the µEforth build. There's a mode that I call a sim mode, where it builds for the host architecture, but with the vocabulary and startup files and forth all sort of mirroring the target architecture. And this is useful for catching situations where something breaks. And I believe I've even used this a few times when I sort of overly aggressively refactored ESP32 for it. It turned out that I had had some failures in the startup. I had assumed certain operations would be present that were not there, and lo and behold, it came up. So it was not a terrible porting effort to get up the initial system. From there, I went ahead and I added bindings for memory and yield and tick support, because those are pretty core, and then POSIX files. And then there's at least for the Pico-Ice, there's a bunch of libraries that they expose that are semi-Pico-Ice specific, related to managing the config RAM. There's managing the flash for the FPGA, controlling the FPGA, controlling the LED, and doing SPI, and then also that 8 megabyte SRAM. So those are just sort of straightforwardly exposed. They're all lumped in one ICE vocabulary right now. One big problem was that it's a pretty slow build. It's not as slow as like the ESP IDF tools, but it gets up there. A couple different things. One thing I noticed almost immediately was that it made my Git repo act very funny, and I think this is related to in newer versions of Git, they've started to default submodules to do, when you do operations like git stat and diff and so on, they'll recurse down into the submodules. So I changed the Git modules option to helpfully turn off some of that, which makes Git behave a little bit better. And then I changed the make file if folks try to build it so that it will do just initialization of the parts of this thing that are needed. By default, it'll kind of, if you recursively pull down all of the dependencies, it's quite a lot of content, and you actually don't need all of that to build. And then one other little gotcha with the CMake build, I was initially just telling it to make, and that was building everything in the entire SDK, which is huge and slow. Building just your target will still build a good bit of stuff, because it has to build a bunch of the libraries that you depend on. But and then the other thing was I found that if I switched out the default, CMake is like a meta builder where it emits make other build systems that you then run. And by default, it will on Linux do make files, and I changed it to do Ninja files, and Ninja is a good bit faster. So that sped things up, and all of that's hidden inside of the outer make file. Did some refactoring of the documentation to at least kind of get it there. For now, it's beta only. I've actually got it up on the µEforth AppSpot site on a separate tab. Folks are welcome to go give it a look. I'll demo it in a moment, but so far this is just the microcontroller piece of it, and I'm interested in using the FPGA. There's also, it's actually kind of neat that it has this separate piece of flash for the FPGA, because that means that there's sort of a raw storage space that I could use for like a blocks file system that's actually kind of in some ways more natural than on the ESP32, where you're sharing with a lot of stuff. So it's sort of a whole separate space. So that might be kind of fun. Also, it's pretty cool that it's able to map multiple different devices simultaneously. So the USB support is pretty nice. So having more bindings for that would be nice. But the main thing I'm kind of interested in directionally with it is to be able to synthesize for the FPGA and forth. This is all now at this point in the talk. It divides into the stuff that is aspirational and is mostly in my head, but I've taken some exploration steps in this direction. There's the particular FPGA on this board is one of the very small handful of FPGAs that have been reverse engineered. The bitstream format for it was figured out by this individual on IceStorm, and there's now a tool chain called Yosis that lets you do open source Verilog, and it's actually even fairly nicely hooked into the dependencies with the Pico-Ice SDK, so you can have a Verilog file and build it, and it's all open tools, which is really cool. There's one of the tools in particular, IcePack, which captures it's a single C file, and it describes pretty exhaustively the mapping between the kind of logical format of the FPGA and the binary format. So the FPGA is filled with a bunch of these LUTs, which are basically a 4-bit or sort of 16-entry lookup table element, and then for each of them they have a flip-flop that you can optionally enable, and then there's clock lines and enables and so on, and you have chunks of 8 of these where they're connected with a carry line, and there's a slightly more efficient routing where if you want to enable a carry and turn it into a ripple adder, you can sort of do that directly. There's a great tool actually online. Somebody's made a JavaScript tool that lets you interactively load one of the outputs for the thing and see it laid out and zoom kind of in and out. And interestingly, this tool I think has actually helped me understand there's a mode where you can see the routing paths, and it helps, I think, helps you visualize sort of how the the grid of hops that you can make when doing routing, and yeah, recommend that. The format of the bit stream is a little bit arbitrary, but not too bad. Within IcePack, there's a single class that kind of does the mapping between what I would think of as like the sort of logical layout and then the physical layout that you would need in the bit stream. Basically, the only, in principle, you could emit it directly to the FPGA with those CRAM, ICRAM functions. The one challenge is that you have to keep track of a CRC as you go, so that will be one challenge, is to sort of, unless you want to generate the whole thing first into a buffer, which takes about 100K, you would have to kind of compute that CRC as you go. This is the layout in sort of the logical structure of it for the one of the individual logic tiles, and here you basically establish what configuration you want for each of the LUTs in that particular tile, and then it's sort of one tile within the C. There's a different configuration for the RAM blocks and for the I/O pins and so on. So my general plan for synthesis is to keep an allocation map of which LUTs and routes have been consumed, and then just sort of greedily grab a LUT when in some sort of carefully constructed DSP DSL for it, and then to kind of keep signals in bundles with a linked list of bus values. The basic idea I've got in my head is something like this, where you'd have a bus and an unbus function that lets you kind of join together a group of wires, and then maybe some way to express a LUT. And then the problem with greedy allocation is going to be that you could kind of paint yourself into a corner. And my current thinking is that rather than doing anything sophisticated, just have user level words to let you sort of move the allocation point around to sort of give it manual hints. So if it collides with something and gets stuck, you would just sort of manually poke it out. You could then define a bunch of words in terms of LUTs and build up half adders and full adders, although that probably wouldn't be a great way to do it, because that wouldn't take advantage of the ripple, the built-in carry line. And then you could use the bus and unbus operations to move around larger chunks of signals and do things like build up a multi-bit adder. And the eventual goal would be a syntax that would let you sort of do almost a little mini Verilog of a sort within a fourth vocabulary. So that's the direction I'm ideating towards. It's time for a demo. Let me go ahead and let's see, I'll start with, let me just bring up, if I can find where that is in my screen. Here it is. So I'll start with, is that visible? I mean, it might be better if
Yeah, we see that.
Let me zoom in on that so that folks have a little better.
That's helpful.
A little better view of it. I'm gonna make sure I highlighted the wrong one, but that's okay. I'll do that one. Okay. So the port is not too bad. Basically, there's a new Pico-Ice directory, and it's got a main similar to some of the others that pulls in the dependencies. I've baked in a fixed heap size because I wasn't able to figure out a good way to figure out how much fourth heap was safe to grab programmatically, but that's a thing to do. There's a little bit of platform specific stuff to hook up the keyboard, the serial input on the device. It uses there's a fairly elaborate way to set up a bunch of USB to serial bindings, and then one thing that it does by default is it will make standard in and standard out appear to be the serial port in the device. So, but then there's this peculiar way that you can query for serial input. Right now there's no auto boot, and so all this is just disabling a bunch of the logic that's there, and then there's bindings for the various words. Let me go ahead and I will go and do fire up. Oops, I'm in the wrong directory for that. Let me go ahead and share. Oops. I've got the, I don't have the board plug. It would help to plug the board in. All right, let's try that again. And let me go ahead and focus on that one just so it's a little bit bigger. and it's regular old µEforth. The floating point stuff just compiled, so there is single precision floating point. I have not looked at all into whether that's software or hardware on this particular chip. Probably good to know that at some point. The only device-specific set of words are in this ICE vocabulary, and so here they are. Right now, so I have it in a state where I had previously flashed the FPGA with content. So, for example, one of the very simple things you can do with the device is just start the FPGA code running, and the program in there is just oscillating through, blinking the LED in various colors. So that's not particularly exciting. You can also do stop and turn it off, and then the interesting bit is the LED is managed sort of jointly between the FPGA and the microcontroller. So you can initialize the LED, which will then cause the CPU to assert control over it. And then if you do, there's separate, for whatever reason, they separate out the red, green, and blue to different channels. So you can enable the individual pins. So you can turn on I'm typing with one hand here, and turn on the green LED. So that's about where that is. One other, I'll take, I guess at this point, I guess I can switch back to the slide. Actually, I'll leave that up there. It's just a question slide at the end. One other random announcement, or I guess a query to the group. I was noticing recently, I apologize, there was someone, I think at the last meeting I attended, who was having some trouble with BTerm. And I just earlier today got around to looking at that finally, and noticed that I'm having a little trouble building some of the older versions of ESP32 with current tools. So I'm curious if folks are having bad experiences with some of the updated versions that are out there. It looks like there might be some subtle incompatibility, including with some of the old ones, but curious if folks are running into stuff. But with that, I'll take questions.
Thank you very much.
Hey, Brad, are you flashing that LED through your own configuration code that you sent to the FPGA?
No. So this is before I put it in, put on µEforth. There was I had the default bootloader, which is able to load a Yosis Verilog generated piece of FPGA code. Because when you reflash there's two separate flash chips for one for the microcontroller, one for the FPGA. So I'm just enabling the FPGA, and there happens to already be something running on it. There are those CRAM words allow a different mode of operation, and there's actually samples of this in the SDK, where instead of getting the configuration for the FPGA from its dedicated flash chip, you can instead have the CPU provide the bit stream sort of directly. And so one of the samples in the SDK literally builds with Verilog to just a data file, maps that turns that into a C header file with a bunch of data, and then sort of serially sends it over. And so and the intention there is that you can actually pause the FPGA, send a new config over from the microcontroller, and then start the clock running against the FPGA. So.
This is really
the synthesis will be tricky, but I'm starting to wrap my head around the layout of the individual the format. My biggest concern is I would rather have the FPGA bitstream be something that I can generate from a smaller config in memory, rather than have to materialize all 100 kilobytes of it
Sure.
Brad, how long are you working with this?
I got the board only 2 weeks ago, so pretty recently.
Yeah, great.
Yes,
great work.
I asked this on purpose.
Yeah, great work. So
It's incredible.
using the C2 chain that you're currently using, that's certainly the Raspberry Pi Foundation way to do it. My understanding is that also the Arduino world supports the Pico as a target board.
Oh,
so wouldn't that be also a way to use ESP32 force, but change the Pico or the development board and use the Arduino toolchain to do everything?
Mm-hmm. I was unaware of it. tells I've been living under a rock apparently.
Yeah.
Oh,
Well,
I thought he went that way. He went through Arduino.
No. He used the Raspberry Pi C++ development environment.
Had I known there was an Arduino one, I probably would have gone that route.
Yeah, I'm not sure whether the Pico-Ice board is supported, but certainly the Raspberry Pi Pico boards are supported, and given that it's compatible, probably yes. But yeah, I wonder what restrictions you actually face. Yeah. Anyway, great work.
Check that out.
Yeah, great work. Are there any other questions? I see so many capabilities in combining FPGA and force system and configuring this on the fly. So yeah, wow, that's great. Questions?
Yeah, fingers crossed I can actually pull it off. There's a good bit from here to there, but it's at least neat to have a board that's sort of set up in a mode where that seems to be a possible mode of operation. So
well, Brad, you have also the Tang Nano, which is from LilyGo, and has an ESP32 and a big FPGA of 9K on board, and it costs only $9.
Oh, what was this? Is the LilyGo one of those? Let's see.
LilyGo FPGA. Let me tell you.
Is it one of the open source? Is it one of the FPGAs that have been cracked though? That's the other challenge.
CPIT Tang.
IPD, yeah.
CPIT Tang Nano.
I think that's a Govin FPGA on there.
Exactly.
So I'm not sure whether it's already supported by users.
Tang Nano is.
I'll check it out.
Mm-hmm.
It has a RISC-V on board.
Yeah, so it's the ESP32 RISC-V version. Yeah. Mm-hmm. Right. Are there other questions for Brad? Bill's clapping his hands. I do this as well. Thank you very much. And right. So then we proceed with our next speaker. And that is actually Bill Ragsdale talking about the floating point conversation, format conversation. So Bill, the stage is yours.
All right, here we go. Let's see, question for Brad. About how much does that board cost and how many hours did it take you to get where you are presently?
So I believe the board normally retails for $35. As I mentioned, it happened to be gifted this one by Christopher Lazinski. I'm trying to think. I didn't spend too much time actually. I think maybe like 3 or 4 hours. It wasn't too bad because, and most of that was just fighting with the slowness of the build of the tool chain and so on. So this is the joy of having a fourth that's implemented in C. The downside, of course, is that now I'm stuck with all of the tools that are slow and adding to the complexity of the build system I've got there already. So.
No, very good. I'll just add a historical perspective. The first kind of super mini computer I ever bought was $60,000 in 1984, and this is incomparably better than that was. We had 50 megabytes of hard drive and about a half a megabyte of RAM, and it was $60,000. So this is light years ahead. All right, thank you very much to all the
that
team
was
out
back
there.
when $60,000 was a lot of money too.
And today's money is like 4x, so it would probably be roughly, say, $200,000 equivalent today. Anyway, enough old history. I'm Bill Ragsdale, the founding president of the Fourth Interest Group and one of the living relics of the Fourth community. And so now we will go to my presentation. Let's share screen. So away we go. Talk today is about examples of floating point conversions. So a little background on this. Where did it all come from? Well, in 1984, a company called Computrack introduced for the IBM PC a stock market analysis program. Graphic, extremely well done, took the investment community by storm. The software itself sold for $2,000. It had a chip you had to put on the back of your computer for secure, and it's about $8,000 today, but it was revolutionary at its time, and the company did extremely well for about 8 or 10 years. It had a data format for its files, and that data format was adopted by many other consumer-level stock market programs. Once you build up a database of dozens, hundreds, or thousands of securities, you want to preserve that database. And this database used a Microsoft 32-bit floating point format, sometimes called QBasic. This is an example of what the program would do. This is the current version, about fourth generations. On the top level, it's showing you a mutual fund, daily price bars, and then a red line of some analysis. And then the three blocks below that are different levels of analysis that are done. So this the company has gone by the boards quite a while ago, and about the third or fourth generation derivative is called a company called Metastock, and it is still using that same 1984 format for compatibility with your data files. Now, I've attempted to use analysis on that, reading those data files with other software such as SysTap, MATLAB, R, and so on. And I've gotten interfaces written, but I've never gone too far on them. But the starting point was to write the floating point conversions into each of those languages. And so now it's Win32's to get that conversion. The first tool I needed was what I call BDOT, and this is a simple diagnostic binary print. It allows me to put in a 32-bit number and look at it in binary where all the bits are identified. So you see the black at the bottom would be bits 0 on the left to 31, bit 0 on the right to bit 31 on the left. So I can pick a word apart because we'll be looking bit by bit at these binary numbers. So here is the original QBasic Microsoft format. It's a 32-bit floating point, and we'll take it from the left-hand edge. The first 8 bits are the exponent, and there's an offset applied to this of 129. So this allows it to handle negative values in a pseudo-positive format. The 23rd bit is the sign bit, and there's a hidden bit. We'll come back to that in just a moment. And then there's the significand. It used to be called the mantissa, back deriving terminology from logarithms, but currently today's days, the actual value is in binary is called the significand. The hidden bit. The significand is left justified, so there's always a 1 bit in the leftmost bit position. Since there's always a 1 bit in the leftmost position, it doesn't need to be expressed, it's implied. So whenever you see a floating point number, the leftmost bit in the significand is actually not there, and you have to restore it in your software. This gives it a slightly, well, it's more than slightly, and this gives it a 2-to-1 range advantage. In other words, you now have a 24-bit resolution done in 23 bits. So let's look at the pseudocode for this. What we want to do is, referring back to that previous bit arrangement, first we want to extract the low 23 bits over bits 0 to 22. We then OR in a 1 in the 24th bit position, which is our hidden bit. We then pass this to a floating point stack. We shift the decimal point 23 bits to the left, because that's where the decimal point is. It's between the hidden bit 1 and the rest of the significand. Then we extract the exponent with a simple masking by hex FF. Right shift that by 24 bits because we want to perform arithmetic on it. We subtract the bias of 129. Then we raise the significand to the power of that exponent using F star star, or a floating point exponential value. We extract the sign and apply that to the final float, and we are done. So here is what the code looks like, and this is Microsoft IEEE. On the data stack we have N, which is the 32-bit Microsoft floating point image. And when we're done on the floating stack, we're going to end up with, should be F there, a floating point number, an 8-byte floating point number in IEEE format. The code comes out fairly linearly. We duplicate the input for future reference. We do a simple mask to pull off the significand, and then we OR in with that 0x008. We're ORing in the hidden bit. We then use some floating point math to do the 32-bit right shift. Next, we're going to the original input and we're masking off the exponent, and then doing the right shift on that so we can compute on it, and then subtracting the exponent. Then using the next line, a 2E single to float, float star star, float star. That scales the significand by the exponent. Finally then, at the very last line, next to last line, the 0x008 is testing the sign. We mask off the sign, and if the sign bit is present, we have a negative number, so we do a floating point negate. This uses very heavily, it's a good balance between all the bit work is done at the integer stack level, and all of the numeric manipulation is done at the floating point. So it's a very good marriage between the two capabilities. In your mind, you are doing some significant juggling between what's on the data stack and what's on the floating point stack. Here's an example. The first line there begins with the 0x8578. That is in Microsoft floating point the number 31. And I use that as a test case because when you look at it in bit form, you'll only see 3 bits, and we know that 31 has 4 bits. Well, the reason then is that floating point bit is not expressed, so in the binary dump you'll only see the 3 bits, and so it's a good number to work at for testing. And sure enough, we look at this we expect 31 and we receive 31, so we've got a good answer. The next line down is the 0x95162888. That in the Microsoft format is a date, and it's converted to IEEE form. We print it out, and sure enough, we see 12300101 in this metastock format. The century is represented by the 1. This is an artifact from year 2K conversions. Originally, they omitted the first 2 digits of the year. Y2K came along, and they had to add something to indicate we're in the 2000 series, and so they simply put a 1 out in front. So again, the long known test Microsoft Word comes in, and sure enough, it computes back to and gives us our date of year 2023, January 1. Let's look at the IEEE format, because now we want to convert the other way. We want to go from IEEE back to Microsoft. So the IEEE format is a double word or 64-bit format. The bit arrangement is different, but fundamentally the concepts are identical. The leading 64th bit is the sign. Then we have an 11-bit exponent, and because it has a wider range, its offset is 132. Then comes the hidden bit, which is in between bit 51 and 52, and then the significand is 52 bits. So that goes from bit 0 to bit 51. The pseudocode to process this says to begin, if the input is a 0, we force 0 as a final float. Now this is a little quirk in floating point, because the number 0 would normally have the implied floating bit set 1, but of course that would give us an answer of an integer 1. So as a compensation for that, whenever a full 0 is encountered, the floating point forces the 0 output. We then copy this float image as 2 32-bit values to the data stack. Now, Win32.Forth provides a word to do that. It's actually an interface word that's used to pass floating point numbers to the Windows operating system. But in this case, the full floating point value is taken from the floating point stack and put in binary format onto the data stack. So it allows us to examine the bits that are in floating point format but on the data stack. Here we're doing something similar we saw last time. We shift the low 32 bits and with 29 bits to the right are filled with zeros. We're also, remember, we're reducing the resolution of this so that the larger significand is just simply truncated to the lower bit count. We then swap the data stack to get access to the high 32 bits of the floating point number. And again, we mask with a 7FF, which extracts the exponent. I do a 20-bit right shift to bring that exponent down for calculation. We subtract the IEEE bias of 1032, and we add the Microsoft bias of 129. In reality, we just make one adjustment for that. Those two numbers are combined into a single number. We don't actually do two adjustments. This exponent is shifted 24 bits to the left to put it in the proper position for the Microsoft format. We extract the sign, shift that 8 bits to the right, because the sign bit is at the extreme left in IEEE and it's 8 bits in on Microsoft. We extract the low 20 bits and shift the 3 bits left to make room for those 3 bits. And now we have we have 3 components on the data stack. We've got our significand, we've got our exponent, and we've got our sign. So these are just ORed together to finish the final number, which ends up on the data stack. Here's our code. It again matches that pseudocode as we see. At the beginning, we duplicate the F-duplicate the IEEE word, test to see if it's 0. If it is, well, we drop it, we put 0 on the data stack, and we exit. So that is a quick exit on a 0 value. the very clever Win32 fourth word FS to DS. That takes the floating point and transfers it directly as an image to the data stack. We then do a 29-bit right shift and zero fill automatically. We then extract the exponent. We do some math on that to on the data stack to translate the exponent. And I've shown here where we subtract 1029 and we subtract 1023 and we add 129. In reality, in the production code, that's one number translation. Move the exponent high, reach over and extract with the 0x8. We extract the sign bit, we shift it to the right where it's needed in the output. The last line down there positions the significand in the proper place, and a couple ORs at the end combines all three of the components into the final result. We're going to test this now by a translation from the IEEE floating point. We'll translate it to Microsoft. We'll take the Microsoft, translate it back to IEEE, and we better get the same answer. So we're testing it in this case with some small numbers. The decimal 0.00001 in floating point translates to Microsoft back to IEEE, and we print it out, and sure enough, we get the right answer. I point out this is a very rigorous test because the calculation processes are quite different between the two formats. So if we had any error in translation, it would be revealed by a major deviation between the two. The second test is with a negative number. In this case, we have a minus decimal 12345, and it translates through double process, and sure enough, we come back out with the required negative 12345. This is an example of the process in use. The upper window shows the database that's taken out of the Metastock program. So this is how the production Metastock system would show the raw data. It gives us the date, the security, price, high, low, and close. This is done on a weekly basis. And in this case, the volume is empty because I use that for yield adjustments. Then in fourth, the equivalent data is extracted from the same file. And in this case, we have in date order is year, month, day. 23, of course, is 2023. First line is June 9th. And we see the same matching high, low, close, and volume. So all is well. Here is a bonus element. I thought I might be doing some of my analysis on the floating point stack and some on the data stack. So I needed to scale the floating point values to a scaled integer value, and I was astounded to see how simple it really is. In this case, the N1 input value is a scaling factor. If you want to scale by 100, you use the number 2 because you want to scale by 10 to the second power. The production code then says 10E puts 10 on the floating point stack. S to F brings in the exponent. We raise with F star star, we raise 10 to the exponent power and then multiply our floating point number, and then finally translate that floating point number to a integer value. And so it turns out very handy. This is an example of use. If we have a floating point number 123.567, the 2 is the desired scaling factor. We translate it and then print it out in from the data stack, and we see, sure enough, we get 12356, 123456, which is scaled by 100. So a few observations on this. As for many problems, when I look back at the actual code, it looks pretty obvious, pretty straightforward, but I'll tell you, it looks a lot simpler now than it did when I was looking at the raw bits. For future stock market analysis, it appears that I'll need floating point for exponentials and integer and bit logic and mod and slash mod for scaling. Otherwise, I have to do some expansions on the floating point, and I'm a little nervous on trying to expand floating point operations, but I'll give it a try. And so at our next session next year, I'll probably give a presentation on the file access and how this actually is used in applications. So for our references, the first is I've already uploaded the source code and the slide series on GitHub. So just go to GitHub Bill Ragsdale. There's two sections there. There's the popular section, and then there is the total section. And so this would be on the total section because it is not yet popular. Here's a fairly obscure reference on the floating point formats. Buried down on this in this section 22.2212, you'll see the explanation of a number of floating point formats. So that concludes my remarks. Do we have any questions?
Excellent, Bill. Fantastic.
Very nice.
Good, you're all stunned. Yes.
Can I speak? I have a remark or a question. You use the 0x prefix for floating point numbers. I thought I was the only one who's doing that. Is that normally used by other person?
Now the convention for 132/4 is the 0x is hexadecimal, so that's the format for a hexadecimal number. Floating point numbers are terminate with an e and the exponent. So if you want the number 10 in floating point, you put 10e. If you want the number 100, you could put 10e2.
Yeah, okay. That's deviating from the dollar that's used in the 2012 standard, so to speak. Okay.
Answer yes, that probably does. Yes.
I like it better than the dollar. So.
Well, I'm stuck in a time warp of Win32/4 because it was released originally around 1995-2000. It has had some small additions, corrections, and enhancements in the time frame 2010 to 2015. But it's extremely stable. When you download it, everybody has the same exact version, and applications are portable easily portable between because it's a very stable system. And we're all done.
That was a great talk.
Thank you very much.
I do have a question. I was trying to calculate an 8-bit floating point, converting it to an integer for FPGAs, and I came up with 9-bit integer. Does that sound about right?
9-bit resolution, you mean? Or?
Yeah, 9-bit resolution, the integer equivalent to an 8-bit floating point.
Well, you just look at your significand and run that to the power of 2. So if you have an 8-bit significand, then it's 2 to the 8th. Although with the hidden bit, you actually get 2 to the 9th.
Okay. Yeah, there's a lot of data out there in floating point that I'd like to process in parallel on an FPGA, and you have to,
Well, Well, a good reference would be go to the source code of Win32.Forth, because you've got the very well engineered, very well reviewed floating point package for that. There's some good brain power that put that together. All done.
I might be missing something, but if there's always a 1-bit implied significant or mantissa, how do you represent 0?
0 is forced to be 0. If you notice on the pseudocode at the beginning of the IEEE conversion, I do a 0 equals, and if it's true, you force 0 in the output. And so,
Okay.
if I understand right, every floating point chip, when it begins a process, checks for 0 at the beginning.
And for IEEE formats, it even is the case that whenever the exponent has the lowest value, the exponent itself is 0, then the hidden most significant bit isn't there, and the number can, the significant can, is unnormalized, is a subnormal number. But that's a quirk of the IEEE floating point standard, and the topmost value of the exponent represents infinity and nans. Nans, not a number value.
No. Well, forcing 0 is the way that it has been done since day one, as far as I know.
Yeah.
Also, we've glossed over IEEE. There are a number of other values, like not a number and largest number, smallest number, and so on, that have special meanings. So we'll refer you to standards on IEEE for that.
Yeah.
Amazing, fantastic, Bill. Now is the turn of getting rich. We want to get rich with force. And then we have the experts from Xiaohui and Greg Worth. They will explain us force and Bitcoin.
How's it going, everyone? It's good. Thank you so much for having us.
Thank you, everyone.
Amazing presentation so far. Really glad to be.
Can we get rich with you, Greg and Xiaohui, or no?
I think you're gonna get rich just by your own geniuses that I already know is in the room. So hopefully Xiaohui and I will inspire the group to take all of your fourth understanding and your reverse Polish stack notation understanding and be able to apply this to Bitcoin script building. So we're excited to give a demonstration. I will give a quick brief overview again for those of you who weren't here last week about Bitcoin script and how it is modeled after the fourth language. I'll share my screen and then I'll turn over the presentation to Xiaohui after. All right. This might be. All right, can you see my screen?
Yep.
My computer's acting funny already. Can you guys see my screen or my?
We do, but we see some black boxes around.
Yeah,
certain...
it keeps on acting funny here. Let me see.
They're gone now. Thank you.
Now. Yeah.
All right, now it's acting. My computer is acting funny. Let's see if I could shut some stuff down real quick. All right, let's try one more time.
Probably could avoid this problem if the problem was written in Forth.
Hey, you know what? I'm gonna stop sharing. I'm gonna probably just go ahead and allow Xiaohui to explain some stuff next. But basically the idea, guys, is that within Bitcoin script, you have a locking code which locks up funds, which you could utilize in a numerous amount of ways. So you could lock up funds to send to somebody, or you could lock up funds that causes another interaction be capable of happening. So let's say that Xiaohui locks up some a 5,000th of a penny, but that person who's able to unlock that funds maybe is able to cause an interaction with one of your fourth systems, right? So if somebody has the private key that unlocks these funds on the Bitcoin network, which is a distributed, decentralized group of validation computers or nodes who all have the same ledger of transactions. So you could set up a situation where for 5,000 of a penny, you could create a smart contract that if someone executes it, it can cause another interaction, let's say with your fourth hardware. Again, I'm gonna actually turn over the presentation to Xiaohui and see if I can get my computer to allow me to share in a little bit. So Xiaohui Liu is from S-Script. He works on Bitcoin script all day long and is really influential in the greater Bitcoin ecosystem in showing some of the more in-depth ways of building these locking scripts, which again is built off of and modeled after the fourth language. So Xiaohui, take it away.
Okay, thanks, Greg. Thanks, Peter, for the invite. Can I share my screen now?
Yeah, go ahead.
Okay. I hope mine works. Is this okay?
Yeah, we see it.
Okay, cool. Yeah, so, hopefully I'm going to show you how to get rich with force, but not in the way you want it, Peter. Okay. So it's not going to buy Bitcoin, but instead using force to program Bitcoin so that you can have, killer apps that millions, even billions of people use. Okay. So if that's one message, get out. I just want to, hopefully I can inspire you to look into how to use your force knowledge and apply to Bitcoin app development. Okay. So short introduction. So my name is Xiaohui, and I'm a founder of this startup called S-Script. So first I'm going to explain, what force role in Bitcoin, and then in the second half of the talk, I'm going to explain what S-Script is. And also, my first time force community, so I didn't know you existed. So thanks, Greg, and bring me to this community. Really glad to meet you all. Yes. So force, how does it relate to Bitcoin? Okay. So as Greg briefly mentioned, the keyword here is Bitcoin. So when Bitcoin first launched, even in the first version, it's not something that added later or modified. It's when it first launched, the first version in 2009, January 3rd. If you look at the Bitcoin code, you have an interpreter, which interprets the so-called Bitcoin script. It's a low-level, kind of like a, let's say, bytecode or assembly-like language, which is inspired by force. Even according to the inventor. The inventor, with the pseudonym Satoshi Nakamoto, he used force, extensively in his career, and most notably, he was in the Australia Royal Air Force, and he wrote code for some of the jet fighter jets. So that's when I first heard about force. Okay, and it was force-like. Of course, Greg also mentioned is reverse Polish notation, and it consists of the so-called opcodes or bytecodes. So just want to give you a very high-level idea without diving into the details. So this is all the opcodes that's has been running in Bitcoin, since the very beginning. You have probably not very real, but on the high level, you can, you guys know force probably, I don't know, maybe even before I was born. Anyway, so you can probably, recognize all of those, if not, most of those, if not all of those. You got the stack, you got the constant here, you can push numbers, 3, 4, 16, or stack operation like do, drop, row, and swap, and tag. And these are all, I think, just borrowed from course. I think we also have some specific that's only you can find only Bitcoin script. For example, most notably you have an operator, you have an opcode to check the signature, because a lot of times when you move Bitcoin, when you to show your ownership of the coins, control, you have to show something like a digital signature. So you also have a commonly used hash like SHA-256, Xiaohui, and also you have let's say Boolean operators, and also conditions, and slicing operators, and arithmetic. So these are all the opcodes I listed here is what the Bitcoin is using. I think is, as you can see, it's very similar, if not entirely based on force. Okay, so that's the connection between Bitcoin and force. And then I'm going to briefly explain which part of the Bitcoin. Right? Bitcoin is a gigantic system. Even from pure technical point of view, it's a sophisticated piece of software. There are many moving pieces, but where does opcode and that's force play into this big picture? Where's the role for opcode? And it's a central piece. So for people who have not heard about Bitcoin, think about it as a digital currency, or some people call it electronic cash. But a lot of people assume you can only do, let's say, payment, right? You can send, let's say, money from Alice to Bob. But it's much more powerful than that. It has so-called programming capability. Okay, so where does a programmable money come from? So just give a level of Bitcoin. When you say you have 5 Bitcoin, it's not like a bank account. You have a balance of 5, Alice has 5, and Bob has 3. So Bitcoin doesn't work like that. It's actually more like you have a cash. You have when you say Alice has $5, so she may have 3 $1 bill and one $2 bill. Okay, so it's scattered around in so-called big transaction outputs. So Bitcoin, at the transaction level, you have Bitcoin transactions. Okay, so transactions and then mined into blocks. So that's why, and the blocks are chained. That's why you have this Bitcoin blockchain. But when you zoom in, you have transactions. So when you zoom in into each transaction, you can see 2 things. One is so-called inputs, and on the right, you can see outputs. Okay, so input, you can think about the money that you are spending, and output, you can think about the money you just created, new money. So each transaction spend outputs from existing transaction outputs, which have not been spent. Right? So that's how you avoid the so-called double spend money, double spend problem. Right? So if I have some money, if Alice sends to Bob, Alice doesn't have the money anymore, right? Because otherwise you can send it to Charlie, Dave. The system just breaks down, right? So that's how fundamentally, that's how Bitcoin, solve one of the biggest. And then the obvious question here is, how do you control who can spend the money locked in some output? Because it cannot be arbitrary, right? If Alice can spend any output that's outstanding in the whole system, it doesn't work, right? Alice shouldn't spend Bob's Bitcoin, okay? So that's where the so-called Bitcoin script or force-like language comes into play. So think about every output, you have some 2 parts. First is the amount of Bitcoin in there. It can be 1, it can be, 200, it can be 0.01, it has amount. And then another important thing is it has a lock. So conceptually, there's a lock that is placed under. So in the input, whoever try to spend the money, spend the Bitcoin here, they have to provide a key, and this key has to match have to be, corresponding key to the lock here. Okay, so how this is the lock that's represented in so-called script. Okay, so this one is also script, but this is only data here. So you can think about this only has push data there. You can only push data. So this is the key, or sometimes you can call it a wait list. So this is the here, that's the locking script here. So what does the Bitcoin system do when you broadcast the transaction here? It's very simple. So how do you verify whether this spending is allowed or not? You concatenate the script here, unlocking script, with the locking script here, and then you run the whole force program. And then if they end up with a true value on the top of the stack, then this is true. You can move the money. Otherwise, it's going to be rejected by the Bitcoin network. So that's a force like Bitcoin script that plays into the central role in the Bitcoin system, because it gives the access control capability. Okay, so I mean on the right is the same thing, but I just show you instead of just two transactions, you have you can have a graph, so-called DAG. We don't have to get the detail, but that's how this probably give you a better idea. Each person some outputs, and they can spend in subsequent transactions, creating new, and this system just keeps going. Okay. By the way, if there's any questions, anyone, just feel free to interrupt. Okay. So if now we just keep going. So just give you an example here. Just want to get a sense how many people use Bitcoin. Anybody here? You guys, none of you want to get rich. Okay. Okay. So you now use, you probably heard about, how many people heard of a Bitcoin address? It's this long sequence of like a gibberish, like string people. It's like a mailing address. People can send you, instead of mail, they can send you Bitcoin address. Anybody? I guess. Okay, that's good. That's good. So this is what actually, what's under the hood when you say you are spending, you are sending some people spending Bitcoin from her own address. Okay. So as I said earlier, the script, you have two parts. One is a lock part, we call it locking script. So in this example, this script code, this is what a Bitcoin address looks like. If you break it down into the script, the force-like language. Okay. So this is the address here. So it's using cryptography, kind of public key cryptography. I assume many of people here already know. So you have a private key and a public key. So the Bitcoin address is simply the hash of the public key. Okay. So when you say you send this address, you're actually sending it. The address is identified by hash, the public key. Okay. And it's locked in this script. Okay. Dupe hash. You have an equal verify based on this. Compare the top two elements, and if they're equal, it just doesn't keep going, pop out and keeps going. If it fails, the whole program fails. Okay. And the check sig is basically, it's like a signature checking, right? In verification in any digital signature scheme, you have the public key, and also you have the message and signature, and it checks whether all check out. Okay. So how do you unlock this address? You provide two things. First is the so-called public key. Second is address. Okay. So you concatenate this unlocking script with the lock, and then you just run them, right, from left, to right. Okay. So I show here a short animated animation that shows how the stacks looks like and what's the remaining of code looks like at any given moment. You can see, this is the force like. I only show one stack because we call it the main stack, and that's actually another stack. Is the same dual stack architecture, same with force. Okay, but instead of calling return stack, the second stack we call it auto stack. Okay, so meaning alternative stack. Okay, so this is what it looks like. You know, it pushes the signature and the public key, and then you just run the code. And at the end, if the signature is coming from the corresponding private key, this is going to check out. Okay, that means the signature matches the address, and this spending can proceed. Okay. So I just showed you, you know, how force-like Bitcoin script works. You know, it plays a central role in the spending of Bitcoin, and that's a slight problem. You know, if all of the programs were they are as familiar as with all the people here, I assume we don't have. You can program all the things in force. Okay, no problem. But that's a slight problem. Okay, that's where, you know, script, the project I'm working on, where it comes from. Okay, so here I just show you some.
Xiaohui, I don't want to interrupt. Apologize. Can you maybe turn off your video? You break. I don't know if the other guys are hearing your audio break up, or if it's just me.
I have it as well.
Yeah, it sounds like your audio is breaking up.
It breaks up.
Amazing presentation, but I just want to make sure the guys could hear you properly.
Is it okay now?
Yeah, that's better.
Okay. Yeah, it all works. Okay. All right. So just give you a sense why, you know, we have the script project. Basically, you know, if you look at all the project, all the so-called programming languages in the world and ranked by the users, we have, you know, JavaScript, Python, which have tens of millions of users worldwide. But I don't know, does anybody here know how many Force developers globally we have? Anybody have a guess? Thousands?
Yeah, I'm imagining not so many these days.
Yeah.
It's probably, probably not 10 million, right? If I have to guess. Okay, probably not. Okay, but somebody can, if they have the number, you can let me know later. But the point is, you know, we think it's elegant, it's efficient, but the only slight problem is not many people, you know, more people should know about it, but they just don't know about it for one reason or not. Okay, so they all know about JavaScript. So that's where we come into the play. You know, you can think about add a high-level language. I mean, I'm going to just tell you here. So called TypeScript. You know, for people who have not heard about TypeScript, it's pretty much JavaScript types with all types. Okay, so a lot of people already know JavaScript, TypeScript. So the idea is, you know, we don't have to teach them force like on script. If they can write the code in TypeScript, and we do some magic. Basically, we compile down Bitcoin script force, so they don't have to learn, you know, force the hard way. You know, reverse polish notation, or you know, all the opcode. They don't have to know any of the stuff. They can just use TypeScript to program, and we do all the hard work of, you know, compile down to force. So the benefit is, as I said earlier, you already have 10 million or even 20 million people who know, you know, JavaScript. So all those people they don't have to know any force to program, which is the native language for Bitcoin. Okay. So for example, I showed you, you know, earlier, you know, here, what is a Bitcoin address looks like. Okay. So this, you can see it's kind of low level and just native force, right? But if you don't know force, you can write it in TypeScript. Okay. I think this is much more friendly, and more people more comfortable with this type of program, especially for new developers, modern developers, young developers. You know, they can just come here and program the same thing, the Bitcoin, you know, address. For example, here, I hope this is kind of readable. You want to, this is the public function you want to call. So this is how you try to unlock it. You give it a signature and public key, and it checks two things. One is hash, matches the address, and second, you check the signature. So this is much more, let's say, accessible, especially for young developers. Okay, so this is where the S script comes into play. It's just, you can think about add this syntactic sugar TypeScript, which we that heavily lift compile down to, so developers they can easily onboard, with program Bitcoin. You have to know about, force. Okay. But here's the thing: if you know force, and if you want to use force to program Bitcoin, you can do it. And as a high-level language is, if you handwrite it, it's like writing assembly versus C++ or Java. Oh, sorry, Go or Rust. It's going to be more efficient, right? So that's why I want to come to this community and encourage people to explore how do you use the force, the native language, you can also code. You don't have to, but this is for more, let's say, young developer, modern developers. For example, right? So we have the, here I show a link. So basically for Bitcoin, because it's a public ledger, public blockchain, anybody can go there and look at all the code and all the transactions. I just show you one example here. So this is one on chain. You can use this block explorer to look at one so-called locking script. Okay, I think this one that's complicated, and not many developers know how to code this using force. But I think people here, you can code this yourself with force. I'm just show you here one example. But what script does is you enable the young developers. For developers who don't know anything about force, they can code in some like JavaScript code. So this is a comparison. So basically the left-hand side comes from compiling of the right-hand side. Okay. So, because it's just TypeScript, JavaScript, so you can, I'm going to not cover the detail, but the short story is you can reuse all of the JavaScript tools. You learn anything about force or how to develop a force, how to debug, you can use it, you can you can deploy the transactions easily, you can debug it with, console log, or even using any JavaScript debugger. You can also manage your page using npm, which like tens of millions of people use it, and you have tens of millions, if not 100 millions of libraries already you can use. Okay. So the last part I want to briefly go over is, you just mentioned all this, force and script, and then what kind of applications people already develop on top of Bitcoin. Okay. So, one is, games. People have been developing games, but I'm not only showing, simple games. For example, is kind of, say, straightforward. If you want to code, let's say, chess on Bitcoin, because chess is so-called a full information game. You know my moves, I know your moves, I know everything all the time, every player, because the Bitcoin blockchain, right, is public. You can see everything, so that's very doable. Okay, but the problem is, how do you do how do you code hidden information game like a poker, right? So it's not very obvious because you have a dilemma. If you put things on Bitcoin, everybody can see, but then it's not poker anymore, right? It's every card, and what's under the deck, your opponent's card, which is not good for poker, right? But if you don't put stuff on chain, then how does the Bitcoin network verify it? So through some kind of like same for Battleship, for people who play this game, you don't know where the fleet of your opponents are, right? So that's what makes it fun. So for this kind of game, you can actually using some kind of advanced cryptography. So you probably heard about it, zero knowledge proof. So actually, you can code this in Forth or in script, and we have coded, and it's gigantic. It's like 1 megabyte of translates to 1 megabyte of Bitcoin script. So so people use this kind of all the tools to develop applications, right on top. Not only you can play game because this is Bitcoin, right? You can also bet on it. It's just make it more fun. And the second one is, big category is finance. So for example, you can issue bonds on Bitcoin. So for people who have not heard about it, you have the Bitcoin, you have the native asset called the Bitcoin, right? On the smallest unit called the Satoshi. But you can also represent, real world asset or off-chain assets. For example, bond, or let's say loan, or options contract. Any type of option contract, option asset, you can also represent it using a mechanism called tokenization. So then you have the digital equivalent of the assets that's not on Bitcoin. You can represent it on Bitcoin. Then you can transfer it, you can trade it, just add for a lot of things that previously impossible before Bitcoin. Then you can put it on chain, and then you can enjoy the same, efficiency of Bitcoin, right? For example, even in the far future, you may even put the title of your car or your house on the blockchain, because at any given moment, it's like Bitcoin. If I transfer it, I don't have it anymore. Okay, so if you can adopt this kind of technology, everything, of course, verified by Forth like Bitcoin script. So the example we put out there with all the running code, you can also check for yourself. This is finance, and this is one of my favorite. So for example, if you want to, let's say Alice, she's very interested in solving Sudoku problem. She's always solving Sudoku, but at one night, this Sudoku puzzle she spent hours on, but still she cannot figure it out. So she said, hey, why don't I put out a bounty to the whole world? Whoever can solve this puzzle, I'm going to pay her 1 Bitcoin. Okay, but then obviously you have the problem, right? So let's say Bob said, hey, I know the answer, just give me the Bitcoin. So Alice pays Bob first, and Bob may run away, right? Bob may not give her the answer, or Bob may not even know the answer. Okay, vice versa, right? If Bob says, I'll give the answer first to Alice, then Alice may not pay him, right? And then what they can do, I don't think you can do it with any other technology. You can put this locking script on blockchain, lock up 1 Bitcoin. And what does this locking script, a Forth program, says? It basically says, is this solution, is this a solution to my Sudoku puzzle? If yes, it checks out, and then Bob can take the money, and then Alice can read the solution. So this thing is called, atomic exchange. So either both directions go through or neither goes through. There's no counterparty risk here. So the same, this is just one type of computation, but you can do with arbitrary computation, right? Logistic, traveling salesman, or even machine learning computation. You can do outsource any type of computation, encode them in Forth, and then to pay anybody in the world trustlessly. I think this is huge. Okay. So, then there are some specific problem in the crypto space. For example, I talk about atomic swap. You may have 2 types of crypto you want to exchange, but you don't trust each other. You can also write some, locking script such that, you can only swap those atomically. So either both of them get the other party's assets, or neither of them. You cannot go just one party gets the other party's assets, but not vice versa. This cannot happen. Or if you want to program some kind of locking script that enables your phone to turn into a wallet, that's as secure. For people who've not heard about, you have the hardware wallet. Basically, the private key is in the hardware. It never gets exposed. It's always offline. So you can actually turn your phone, if you smart enough, you can program force like Bitcoin script and turn your every phone into a wallet that's as secure as a hardware wallet. Okay. And lastly, last slide, I just want to show, where force come from. Okay. It all comes from this quote, by the inventor of Bitcoin, Satoshi Nakamoto. So in 2009, he posted this in a forum. Basically says, Bitcoin is not only for simple payment from one address to another address. It wants to design it so flexible to have arbitrary complex, transaction types. In this case, arbitrary locking script can enforce arbitrary spending condition. For example, you require 2 people sign out of 3, or you can say, I have this escrow, or have a bounded contract, or you have, you can program games, you can program finance, outsource computation. So that's where he wants to, why he put force, breathe it into Bitcoin since the very beginning. Okay. I hope this gives you some, inspiration to explore, the joint of Bitcoin and force, and see what kind of, force program you guys can build, with or without S. Okay. Thank you very much. I'm happy to answer any question.
Thank you.
Thank you very much.
That was awesome, Xiaohui. Yeah. Incredible. I hope that, like Xiaohui said, you guys are inspired by that. I feel like maybe you don't realize that some of all these new things that are being built, it feels like we're back in the 1980s again, building architecture from the ground up in a lot of ways using blockchain technology. And I feel like this group here is so far ahead in thinking, being able to think about fourth script stacks like you saw Xiaohui exemplify. So it's truly exciting. I hope that you guys get involved. But I'm going to turn it over. I hope that some people ask some questions. Thanks, Xiaohui.
Thank you, man.
Is this scripting on the normal blockchain, on the normal Bitcoin blockchain, or are there specific forks that kind of use this?
So the original Bitcoin protocol had all of these opcodes enabled. The current Bitcoin that people see as BTC, that it's the most looked at as so-called Bitcoin, does not have these non-standard scripts, as they call them, available to utilize now, or at least the miners won't mine them. They won't validate them. But BSV, Bitcoin Satoshi Vision, is the one that is most capable of executing these smart contracts. But as Xiaohui pointed out, because of that, you're able to utilize the BSV blockchain with all of the original Bitcoin opcodes enabled to interact with other blockchains for atomic swaps and utilize it for the original Bitcoin. But Xiaohui, do you want to add anything to that?
Yeah, great question. So, as I showed at the very beginning, I think in the original Bitcoin, there's about 100 of those. So for Bitcoin, it's a little bit complicated. You can think about it's almost like a species. And then later on, we have evolved into, let's say different forks or different species. We have the Bitcoin core, which, have some opcodes, but they disable a lot of opcodes. For example, you cannot multiply 2 things, not concatenate 2 things. So I think it disabled maybe like 25% of the opcodes are there. So that's the Bitcoin core fork. And then So Greg and me, we work on the Satoshi Vision, which has all the opcode intact. So the one example I show here, this one is 100% of all the code you can work on the blockchain today.
Mm-hmm. And so on the, I'm sorry, Albert, you raised your hand. Go ahead.
Any library for JavaScript that we can script?
Say that one more time, Alvaro. It was hard to hear you. Were you asking for where?
Oh, sorry.
I didn't realize I was on mute. Alvaro, can you repeat yourself?
You could indicate any library for JavaScript that we can trust in that.
Yep. Well, Xiaohui's got on the screen right now, the script libraries URL. script.io is his library that compiles the TypeScript into the Bitcoin script. And there are also there's also a JavaScript direct library that you could also access if you want to do direct script writing. Xiaohui, you could utilize script to directly write script as well, right? Without relying upon the abstracted.
Yes, so we have two modes, for, let's say, most users, they just use JavaScript, TypeScript, but we also know that people, who are people expert in Bitcoin script or Forth, like you guys here. We also have this like inline assembly mode. You can code, Bitcoin script, Forth directly to, if you know what you're doing. So we enable two, but that's for more advanced, but that's a way to do it too.
Mm-hmm. So Albert, you raised your hand. Please go ahead with your question.
I wonder if I want to transfer $1 worth of Bitcoins, how many megaflops are spent by the various machines? What process that transactions, or many mega operations or giga operations?
That's a great question, Xiaohui. I don't know if you may want to take that one. As far as each node is going to be validating the transactions. So I guess it's a fair amount of validation happening, but the consensus is happening once it's executed and it's added to a block, then that hash becomes part of that block hash, and so it's verified across the network. But as far as, were you asking how much energy is spent or how much processing power? What were you asking?
Let's say processing power.
So, I mean, it's actually an interesting question. I guess, again, I don't know if this addresses this. Our company that I work with, Smart Ledger Solutions, we're developing a Web3 CO2 energy index comparing the various blockchains. And so you have proof of work as a consensus mechanism that validates this decentralized network. That particularly is very secure in its mechanism, its protocol mechanism, but it's also energy intensive. So BTC, as Xiaohui pointed out, the protocol that has limited a lot of the opcodes, because a lot of people are speculating on that asset, so to speak. There's a lot of hash power, a lot of miners that are attempting to win Bitcoin. In our BSV protocol, we utilize the same SHA-256 consensus mechanism for the miners, but we enable an unbounded block size. So whereas the BTC blockchain limits their block size every 10 minutes to 1 megabyte, you can only fit so many transactions inside of that block. So each amount of energy that is spent every 10 minutes on those 1 megabyte worth of transactions is going to be individually transactionally footprint wise a lot. But within BSV, as an example, because we have unlocked and created an unbounded block size, we allow the network to expand and the block size to expand as the network grows. So currently, whereas BTC has 7 transactions per second, I think Xiaohui, what's the most that we've done publicly? Do you know?
3,000.
3,000?
Yes.
Okay. Well, I know that we've done some testing publicly with 50,000, right? At different times, but either direction. So as Xiaohui's pointing out, I mean, we're pushing 3,000, and we're going to be testing, I mean, millions of transactions per second. So as the network expands and the block size expands, each transaction becomes extremely low in a footprint. For instance, at 2 million transactions per second, which is certainly capable moving into the future, we surpass a per visa transactional footprint for processing. And granted, the opcode and the extensiveness of the opcodes and what the miners are going to have to do with their machine in order to push these opcodes and verify it is going to certainly increase the consumption and the CPU usage. But anyway, I hope that it explained a little bit as far as the amount of energy that's used both within the Bitcoin network per block, but also that last piece is each opcode certainly is going to make a difference on the processing power.
But I understand that my transaction is processed in parallel through a block. So it is not easy to understand how the energy consumption or the operations for an individual transaction is. Is that right?
Yeah, well, you have two things CPU wise that's happening every 10 minutes. So you have within the Bitcoin protocol, you have the transaction validation, which would be a let's just say a computer validating the opcodes to see if they evaluate to true, and then that means if the person had the right to unlock that Bitcoin and make the transaction, then it gets published into that block if it's valid. That's one operation or series of operations, which is what Xiaohui is showing right now. The other operation is the so-called hashing in order to win the reward or win the ability to place the block on the chain. So let's say that every one of us in this group here has a mirror image of the block chain, the current state of it. Then at the very top of it, we have the hash header. So if anyone tries to change anything underneath it, we'll just reject them as being false. So we have to assume that everyone is being honest. If we see the hash header is the same, now we're all hashing away, trying to find a random hash that allows us the winning ability to place that block on the end of that blockchain. That consumptive power is what people oftentimes argue against as being consumptive within Bitcoin. But that investment into the energetic consumptive power of hashing, if you will, gives you kind of a peacock feather to show that you're actually putting investment into your mining operation, so to speak. So that's what provides the economic incentive to say, if I see that the hash power that you're providing and you win a block, I'm going to say, okay, well, you've invested enough energy into that. I'm going to assume that I'm not going to assume it, but I'm going to see you as being more honest. If you are expending all that energy and you try to put a false block into the blockchain, all of our hash headers are going to show that your hash header mismatches. We're going to reject your block, and you're going to have spent all that energy for no reason whatsoever. So it's a combination of this economic incentive of winning the reward for all the transaction fees for everyone's transactions in the block, plus the block subsidy reward that currently is in place. So the energy is both twofold. It's the validation of the transactions as well as the computation to win the block reward or win the chance to put the block on the blockchain. But again, so in calculation, if you were to take all of the hash power right now that's currently on BTC, which is 98% of the hash rate, I think, worldwide, and apply it to a single public ledger, it would only have to be processing about 2.5 million transactions a second, which, again, if you think in terms of worldwide finances and supply chain management and all these different industries, it would very quickly go below, again, something like a Visa transaction, which is, you know, I mean, oftentimes seen as very green compared to a blockchain. Again,
Okay.
I don't know if I answered your question at all.
All right. So Don has raised his hand, and then Christian as well. Don, please.
Yeah, I have a couple of questions. First one is, anyone building like an ASIC or an FPGA that is specifically designed to be servers on the network that would maybe run at lower power versus a general purpose computer?
Definitely. Yeah. ASICs have been in place now for a while, probably since what, 2015, Xiaohui?
I think that's I think that's a mid. Let me explain two things. Okay, first one is, as Greg briefly mentioned, what the Bitcoin system mostly, the so-called miners mostly have two tasks, two things to verify. First one is, I think he has to verify this Bitcoin script. You know, he run this kind of the script and run, check whether it's true, right? So that's the computation part of things to verify transaction. The other part outside this transaction is so-called, you know, you are doing this crazy hashing, the miners, you know, that's where the energy come from today. It's probably 99% is from finding that specific hash that has a crazy amount of leading zero, let's say 100 leading zero, because that's where the most energy come from. Okay, I think for that part, it already has a hardware acceleration. At the beginning, you know, when Satoshi first releases, you and me, we can mine this on our laptop. And then later on, people have FPGA, and they have, GPU, and then FPGA, and now everybody uses ASICs. It's impossible to mine on a personal computer right now. But for the second part, which is running the fourth program, the script, still there's no hardware acceleration as far as I know, because the reality is just the transaction volume has not been that, huge to to justify the cost. I think that's my assumption. I think as the volume pick up, let's say, if you only have 5 transactions, you run 5 this simple program, you don't need hardware, right? You can run this on even a phone. But as Greg is saying, as the scale keeps increasing, let's say one day we get to millions or even 10 million transactions per second. I think that's when the hardware acceleration can come into play. And this is going to be, Peter is asking me even before this, can you become rich after listening to this talk? Yes, not by buying Bitcoin, but if you can, let's say, a very good hardware acceleration like FPGA that can process the script much faster than your competitors. You can sell to miners, you can run it yourself. It's like the hash. I think it is coming in the pipeline, yes.
Okay.
So you're sending source code over the network that is being compiled and executed on hardware nodes. Is that correct?
Hardware, what do you mean? Is a specific FPGA kind of ASICs or? So right now
are your scripts your scripts have to be local to a computer that is tied to your network. So is the computer grabbing data from the network, chewing on it, processing it and throwing it back out on the network? Or are you sending source code like strings across the network to be run on another node somewhere else?
The latter.
Another
Basically,
computer somewhere else.
Yes, you have to send the source code in force, Bitcoin script, to the other, your peer node. They have to
So
run
you're
it to.
going to send string packets on the network to another computer that executes your code on the other computer.
Yes.
Okay. Thank you.
That's where the Bitcoin system is different from, let's say, Visa, right? Because Visa, I don't know source code they're running. They check if they think this transaction is good, it's good. I don't have a way to independent verify. The point is everything you can verify. If you don't trust the miners, you can verify it yourself. Okay, by running this locally.
Right. Thank you, Christian. You have a question.
Hi. I knew absolutely nothing about Bitcoins before I listened to this. What I got of your presentation is essentially that Bitcoin transactions are handled through a fork-like language. And this fork-like language the transaction can really be translated to fork-like language by some form of JavaScript. That's what I got of it. But all this runs on something called a chain, and I have no concept of what the chain is. Could you explain it to me?
Okay, yeah, great. So chain, you think about, because at the individual level, you have Bitcoin transactions, right? For example, I showed here. You have, this is you can think of this as a smaller unit of if I send you some Bitcoin, what I'm creating this transaction, I probably have signed, and then I submit this to the Bitcoin block, the blockchain network. Okay. But you probably heard about every 10 minutes on average, the network is going to group these transactions into
you're
a
breaking
block.
up a little bit.
A what?
You're breaking your audio.
Let me actually maybe stop my video too. How about now? Is it
much
better?
Yeah,
much better.
Okay. Okay. I should turn myself off. Anyway, so once you broadcast the transaction to the network, every 10 minutes on average, the network is going to group all the pending transactions and put them into a so-called block. Okay. And because every 10 minutes or so, you have one block, and how does it connect them? You use hash, right? So in the second block, you have the hash of the first block. That's how they chained together. So that's why they call it blockchain. Does this make sense? So I think you're muted or something.
Christian, you're muted.
Okay.
Yeah, it makes more sense now that I have a picture of what the chain is. I probably don't understand completely how it works, and it's better that I don't. But at least now, Bitcoin is not just a sacred word that I have no concept of. So thanks for explaining all this.
Yeah, hopefully it give you some, let's say, just it's very interesting. Basically, what I'm saying is, especially you're interested in how it works, not only just at the monetary aspect, even the technical aspect. That's what we are mostly interested in.
What I found very interesting is that it's not only related to finance. It could be related to games. It could be related to any form of secured exchange of data.
Perfectly said, Christian.
Yeah, you got it. You got it.
Yeah,
very nice.
So just to repeat Xiaohui's statement, so as far as the blockchain, and also see Alvaro had a chain of hashes, how it could be verified. So two things. One, when I submit a transaction with these opcode scripts inside of it to a miner, at that very moment, the miner is going to verify it and send me back a rejection or a verification that it passed validation, meaning that my signature was able to unlock a previously unspent amount of Bitcoin and now create a transaction, sign it, they verify it, and then they say it's good. At that moment, they're going to share it with all other miners across the network, so they all have a copy of it. So that way, in this next 10 minutes, when one of us has the abilities to place this block of 10 minutes worth of transactions onto the chain of blocks, we'll all know that we all have the same copy of the current state. All those transactions together are hashed. Like each transaction in and of itself is a hash of the transaction. So your transaction ID is a hash of the internal of the transaction. Then all those transactions are hashed to create the hash header, which is the block, the hash of that block. Each block has the hash of the last block inside of it, which is why it's called a blockchain. You're able to verify from the very last block all the way to the very first block that everything is intact through that last hash. That's how you can verify Alvaro.
All right.
Yeah, just to put this more visually appealing, I didn't put this slide. So basically, let's say Bob is e-commerce site, and Alice wants to buy, let's say, a laptop or whatever, things from Bob, and Bob happen to accept Bitcoin as payment. So after Bob ships the good, and then Alice is going to say, hey, let me broadcast my transaction paying you. So once Alice has created this transaction, give it to Bob, Bob is going to broadcast it to the network. The networks, miners, we call it Bitcoin miners, because they're like the old school mining. They're trying to mine Bitcoins out of the existence. And then once the miners get it, they do two things. First one, as I said before, they're trying to find a long string of hash that have 100 zeros or even 126 zeros. Crazy amount of computing work to find this, the pre-image. Okay, so that's number one. We are not worried about this in this talk. We are mostly focused on the transaction validation. How does it verify whether the transaction is good? It runs the force code, right, to check whether this returns true. And if this returns true, it's going to put in the block that he's mining, and this block all chained together through hashes. So that's how the Bitcoin so-called block. So this is one block, and this all consists of individual transactions. I hope this makes more sense, because it's you got a diagram, a picture.
Yeah. Explain a little bit more. David, you raised your hand.
Thanks, Ulrich. Yeah, so I said in the cafe that my background was business, not technical. And although I've been retired a few years, I think it's worth mentioning that with blockchain, there are lots of use cases for traceability. So, for example, I'm speaking to you from Scotland, which is well known for its whiskey industry. You pay a lot of money for a bottle of whiskey. It would be nice to know that it's genuine. And it's entirely feasible using this technology that you as a consumer could walk into a supermarket or a liquor store, or whatever the term is in whichever country you're joining the call from, scan the barcode on a bottle of whiskey and be able to track it all the way back. What was the lorry that delivered it to this store? Who was the wholesaler who sold it to the retailer? At which port was it imported into my country? Which container ship was it on? Which container was it in? Which port did it leave Scotland from? Which vehicle took it from the packaging plant to that port? All the way back to, and then beyond the bottling of that whiskey, even to the raw materials, the ingredients that went into it. There are other people talking about using it for tracing, properly raised beef. So, you could scan the barcode on if you pick up a pack in a supermarket for a beef steak, being able to trace back to which farm that cow grew up on and what it was fed and what its environment was like. Was it factory farmed or was it free grazing? All that kind of stuff. Really interesting business use cases for this technology.
Yeah, you nailed it, David. We have within our ecosystem, I mean, we're just within Smart Ledger, we have our partner, SmartGrow Agritech, that we work hand in hand within here in Virginia, doing IoT collection within hemp fields for verification for carbon credits, but also for verification, as you said, of the cannabis and the hemp industry. He's also working with the wine industry to do the same thing with what, as you described, having labels that you could verify from the vineyard to the table. I would love to connect with you after the call if there's interest. We've got some partners who are working within the cigar industry and other industries with RFID connected to blockchain addresses for the same thing. Yeah, it's. I mean,
just
really,
want to add.
Go ahead, Joey. No, go ahead.
Just add one more example. We have another, company in the ecosystem called Unisort. It's based in Norway. So they are using exactly this technology, not tracing whiskey, but salmon, because that's one of the biggest export. Imagine you can go to some supermarket, you just scan a barcode, you can know where the fish is come from, whether it's a farm, raised or is from the actually in the wild. You can know where it's transported, the temperature, even specific which warehouse it goes to. You can check all these boxes, to make sure what you are eating is actually authentic Norwegian salmon, not some locally farmed one that's claimed to be from there. So yes, as you said, it's the message here is not only for finance, it's not only for payment. Yes, it's like internet. You can apply it in all kinds of industries. For example, the supply chain, right? Gaming or accounting. All kinds of industries can use this.
Well,
okay.
And Christian nailed it. It's for data integrity. It's for the ability, and as David said, to source the origin of that data and be able to verify it with signatures. It's really, incredible.
Especially this is also a good use case for the luxury brands, right? Imagine if you're as rich as Peter here, you buy, some fancy watch, right? You really want to make sure it's coming from Switzerland, okay? And it's not easy in today's world because, for a lot of you, it's offer potential. Let's say you buy some Gucci bag or you buy some, some fancy Swiss, watch. And then with this, you can scan a barcode. And you can actually know it's coming from, it's authentic. It's not some fake one.
Right, Christian again.
Yes, I watch all this and I see those miners that sit at the top of the existing slide. And this is all more or less, those miners are distributed network. They're distributed on a network, probably the internet or something.
Yes.
And what happens if the internet disappears? Are the objects being...
Bitcoin breaks.
Yeah, Bitcoin breaks, but I think we got bigger problems to worry about at that point.
Okay, but does the object that has been stored locally on whatever device I have to store it still something that could be processed outside of an internet?
Absolutely. But so it's two things. So if let's say that the internet goes down and you had a local source of the latest state of the blockchain, and then the internet goes back up, and then we are able to verify the state, why it could jump right back into running again all you need is one honest miner to restart the network from where it was. But you could also go off chain. Let's say we go into the jungle, or we go into, you know, I mean, somewhere that just doesn't have internet, and we have our latest state of our personal unspent transactions. So I'm Christian. I go out into somewhere where it's got no internet. I want to send my cousin some Bitcoin, or I want to make a transaction. I could, if I've got my transaction ID, my and just all the information I need essentially to create that transaction, I could generate this transaction, and then once I get back into service, I could publish that transaction, and it will verify on the network. But the person who I sent it to, who's off chain still, their wallet or their address, you know what I mean, will have those received funds once they get back in service, right? So the network has already validated this transaction. You could generate it off chain. Once you get back on chain, you could publish it.
Okay, it answers my question. Thanks a lot.
Okay, are there any further questions? Okay, this doesn't seem to be the case. So thank you very much again for the
awesome.
talk and the explanation afterwards. That shed light on the things that you're trying to accomplish. So thank you very much. And this concludes our formal part of the meeting with the talks. So everyone, thank you very much for watching this channel, and for everyone who gave some presentation and gave some insight. We continue with the fourth cafe, but this will not be recorded. We can continue discussing different things that we raised during the official meeting. So let me see. I stop the recording right now, and see you soon.